The Milky Way is not just a galaxy. It is a cosmic tapestry woven with mysteries that stretch beyond our wildest imaginations. Picture this: a vast expanse of stars, planets, and celestial phenomena, each holding secrets that challenge everything we think we know about the universe. But what if I told you that hidden within this glittering spiral are objects so strange, so baffling, that they defy explanation? From stars that devour their neighbors to planets made of diamond, the Milky Way is a treasure chest of cosmic oddities waiting to be uncovered. In this journey, we'll explore 50 of the most bizarre and enigmatic objects ever discovered in our galaxy. Each one tells a story of creation, destruction, and the endless wonders of space. So, are you ready to dive into the unknown, to unravel the mysteries that lie hidden in the depths of the Milky Way? Stay with us, because by the end of this video, you'll see our galaxy in a whole new light, and you might just question everything you thought you knew about the universe. Let's begin. Now, let's turn our attention to one of the most fascinating and eerie objects in the Milky Way, the Black Widow Pulsar. Imagine a cosmic predator lurking in the darkness of space, slowly devouring its companion. This is no ordinary star. The Black Widow Pulsar is a neutron star, an incredibly dense remnant of a supernova explosion, spinning at dizzying speeds and emitting intense beams of radiation. But what makes it truly unique is its deadly relationship with a nearby star. Over time, the Black Widow Pulsar has been siphoning material from its companion, gradually consuming it in a process that astronomers call stellar cannibalism. Discovered in the late 1980s, the Black Widow Pulsar immediately stood out as a peculiar object. Its name comes from the Black Widow spider, known for the female's tendency to consume its mate. In this case, the pulsar's intense radiation and gravitational pull are slowly eroding its companion star, leaving behind a trail of destruction. This behavior has provided scientists with a rare opportunity to study the dynamics of binary star systems, pairs of stars that orbit each other. By observing the Black Widow Pulsar, astronomers have gained insights into how these systems evolve and how one star can dramatically alter the fate of another. But the Black Widow Pulsar isn't just a cosmic oddity, it's a window into the extreme conditions of the universe. Its rapid rotation and powerful magnetic fields generate some of the most intense radiation ever observed, offering clues about the behavior of matter under extreme pressure and gravity. As we continue to study this enigmatic object, we're not just learning about the Black Widow Pulsar itself, we're uncovering the secrets of how stars live, die, and interact in the vast expanse of the Milky Way. And this is just the beginning. Next, we'll explore another mysterious object that challenges our understanding of the cosmos, the Great Annihilator. Now, let's journey deeper into the heart of the Milky Way, where another cosmic enigma awaits: the Great Annihilator. Nestled near the galactic center, this mysterious region is a battleground of matter and antimatter, two fundamental opposites that annihilate each other upon contact, releasing bursts of energy in the form of gamma rays. This phenomenon is as dramatic as it sounds, and it's one of the most intriguing puzzles in modern astrophysics. The Great Annihilator was first detected in the 1990s, when astronomers observed an intense source of gamma rays emanating from the direction of the galactic center. What makes this region so fascinating is the sheer scale of the annihilation process taking place. When particles of matter meet their antimatter counterparts, they don't just disappear, they transform into pure energy, creating some of the most powerful gamma ray emissions in the galaxy. These gamma rays provide a unique window into the behavior of antimatter, a substance that remains one of the most elusive and poorly understood components of the universe. But where does all this antimatter come from? That's the million-dollar question. While matter is abundant in the universe, antimatter is incredibly rare, making its presence near the galactic center all the more puzzling. Some scientists believe the Great Annihilator could be linked to the supermassive black hole at the Milky Way's core, Sagittarius A star. The intense gravitational forces and energetic processes near the black hole might be generating antimatter, though the exact mechanisms remain a mystery. Others speculate that the antimatter could originate from exotic processes, such as the decay of dark matter or the remnants of ancient stellar explosions. Studying the Great Annihilator isn't just about solving a cosmic riddle, it's about understanding the fundamental nature of the universe. Antimatter plays a crucial role in theories about the Big Bang and the early moments of the cosmos. By observing how matter and antimatter interact in this region, scientists hope to uncover clues about why the universe is dominated by matter today, rather than an equal mix of both. It's a question that goes to the very heart of our existence. As we continue to explore the Great Annihilator, we're reminded of how much we still have to learn about the cosmos. This region challenges our understanding of physics and forces us to rethink what we know about the building blocks of reality. And with that, we're ready to uncover another cosmic mystery: fast radio bursts, one of the most baffling phenomena in the Milky Way. Now, shifting our gaze to another cosmic puzzle, we encounter the enigmatic fast radio bursts, or FRB. These fleeting bursts of radio waves last just milliseconds, yet they pack an astonishing amount of energy equivalent to what the sun emits in an entire day. First discovered in 2007, FRBs have since become one of the most perplexing phenomena in the Milky Way, leaving scientists scrambling to uncover their origins. What makes FRBs so mysterious is their unpredictability. Some bursts occur just once, while others repeat at irregular intervals, adding layers of complexity to their study. The signals travel vast distances across the galaxy, often originating from regions far beyond our own cosmic neighborhood. This has led to a flurry of theories attempting to explain their sources. One leading hypothesis suggests that FRBs could be linked to highly magnetized neutron stars known as magnetars. These dense stellar remnants, with magnetic fields trillions of times stronger than Earth's, might produce the intense burst as they undergo sudden releases of energy. Another intriguing possibility is that FRBs could be the result of cataclysmic events, such as the collision of neutron stars or the collapse of massive stars into black holes. These violent processes could generate the powerful radio waves we detect. Yet, despite these plausible explanations, the exact mechanisms behind FRBs remain elusive, leaving room for even more speculative ideas. Some researchers have even entertained the notion that FRBs could be signals from advanced extraterrestrial civilizations, though this remains a fringe theory with little supporting evidence. The study of FRBs isn't just about solving a cosmic mystery, it's about expanding our understanding of the universe. These bursts act as cosmic probes, traveling through the vast expanses of space and interacting with the material they encounter along the way. By analyzing how FRBs are distorted as they travel, scientists can map the distribution of matter in the galaxy and even measure the density of the intergalactic medium. This makes FRBs not just a puzzle to solve, but a powerful tool for exploring the cosmos. As we continue to unravel the secrets of fast radio bursts, we're reminded of how much remains unknown about the universe. These fleeting signals challenge our understanding of astrophysics and push the boundaries of what we thought was possible. And with that, we're ready to explore another cosmic wonder, the Boomerang Nebula, the coldest known place in the universe. Now, let's turn our attention to a cosmic marvel that defies the very laws of temperature, the Boomerang Nebula. Located approximately 5,000 light-years from Earth, this stunning structure holds the title of the coldest known place in the universe, with temperatures plummeting to a bone-chilling -458 degrees Fahrenheit. That's just 1 degree above absolute zero, the theoretical limit where all molecular motion ceases. But what makes the Boomerang Nebula truly extraordinary isn't just its frigid temperatures. It's the way it challenges our understanding of how such extreme conditions can exist in the cosmos. The Boomerang Nebula gets its name from its distinctive shape, which resembles a bow tie or, as the name suggests, a boomerang. This unique appearance is the result of a dying star at its core, expelling gas at incredible speeds, up to 164 kilometers per second. As this gas expands outward, it cools rapidly, creating the nebula's icy environment. What's fascinating is that this process isn't just a random occurrence. It's a critical phase in the life cycle of stars like our Sun. As stars exhaust their nuclear fuel, they shed their outer layers, forming planetary nebulae. The Boomerang Nebula represents one of the earliest stages of this transformation, offering us a rare glimpse into the final chapters of a star's life. But the Boomerang Nebula doesn't just teach us about stellar death, it also reveals the intricate dance of energy and matter in the universe. The extreme cooling effect is caused by the rapid expansion of gas, a phenomenon known as adiabatic cooling. This process is similar to how a spray can feel cold when you use it. As the gas inside expands, it loses energy and drops in temperature. In the case of the Boomerang Nebula, this effect is amplified to cosmic proportions, creating a natural refrigerator in the depths of space. What's even more intriguing is that the Boomerang Nebula's shape and temperature challenge our expectations. Most planetary nebulae are spherical or have symmetrical structures, but the Boomerang's bow tie appearance suggests the presence of a binary star system at its core. The interaction between two stars could be shaping the outflow of gas, creating the nebula's unique form. This raises questions about how common such systems are and how they influence the evolution of stars and their remnants. As we study the Boomerang Nebula, we're not just observing a cold, distant object, we're uncovering clues about the processes that shape the universe. From the birth and death of stars to the intricate interplay of energy and matter, this cosmic wonder reminds us that even the coldest corners of space hold secrets waiting to be discovered. And with that, we're ready to journey deeper into the heart of the Milky Way, where the galaxy's most massive and mysterious object awaits the supermassive black hole at its center. Now, let's venture into the very heart of our galaxy, where an object of unimaginable power and mystery resides, Sagittarius, a star, the supermassive black hole at the center of the Milky Way. Discovered in the late 1970s, this colossal entity has captivated astronomers and reshaped our understanding of galactic dynamics. With a mass equivalent to 4 million times that of our Sun, Sagittarius, a star, exerts a gravitational pull so immense that not even light can escape its grasp once it crosses the event horizon. But this black hole isn't just a cosmic vacuum, it's a key player in the story of our galaxy. The discovery of Sagittarius, a star, was a monumental achievement in astrophysics. By observing the motion of stars near the galactic center, scientists noticed something extraordinary. These stars were orbiting an invisible, incredibly dense object at astonishing speeds. This invisible giant, later identified as Sagittarius, a star, revealed itself through its gravitational influence, proving the existence of supermassive black holes. Today, it stands as one of the most studied objects in the universe, offering insights into the nature of black holes and their role in shaping galaxies. But what makes Sagittarius, a star, so fascinating isn't just its size. It's the way it shapes the Milky Way itself. The supermassive black hole acts as a gravitational anchor, holding the galaxy together and influencing the orbits of billions of stars. Its immense gravity also creates extreme environments where matter is heated to millions of degrees as it spirals inward, emitting powerful X-rays and radio waves. These emissions provide a window into the chaotic processes occurring near the event horizon, where the laws of physics as we know them begin to break down. One of the most intriguing aspects of Sagittarius, a star, is its relatively quiet nature. unlike some supermassive black holes in other galaxies, which devour matter voraciously and emit enormous jets of energy, Sagittarius A star appears to be in a dormant phase. This raises questions about its feeding habits and the conditions required to awaken such a cosmic giant. Could it one day become more active, or is this its natural state? The answers lie in ongoing observations and future discoveries. As we study Sagittarius A star, we're not just exploring a black hole, we're unraveling the story of our galaxy's formation and evolution. From its role in shaping the Milky Way structure to its influence on the stars and gas swirling around it, this supermassive black hole is a testament to the power and mystery of the cosmos. And as we continue to peer into its depths, we're reminded that even the darkest corners of space hold the keys to understanding the universe. Next, we'll turn our gaze to another cosmic wonder, the cannibalistic stars of Omega Centauri, where stellar survival takes on a whole new meaning. Now let's shift our focus to a cosmic phenomenon that sounds like something straight out of a science fiction story, the cannibalistic stars of Omega Centauri. This massive star cluster, one of the largest and brightest in the Milky Way, is home to a population of stars with a dark secret. Some of these stars appear to have devoured their neighbors, growing larger and more massive in the process. This bizarre behavior, known as stellar cannibalism, offers a fascinating glimpse into the chaotic and competitive nature of star clusters. Omega Centauri is no ordinary cluster. With an estimated 10 million stars packed into a relatively small region of space, it's a bustling stellar metropolis. Its sheer size and density make it a unique laboratory for studying stellar interactions. Unlike most globular clusters, which are made up of stars of similar age and composition, Omega Centauri contains stars with a wide range of ages and chemical properties. This diversity suggests a complex and turbulent history, one that may involve multiple mergers with smaller clusters or even the remnants of a dwarf galaxy. At the heart of Omega Centauri lies a mystery, a population of stars that are unusually massive and bright. These stars, known as blue stragglers, defy the typical rules of stellar evolution. They appear younger and more energetic than their neighbors, despite being part of the same cluster. How did they get this way? The leading theory is that they are the result of stellar cannibalism. In the crowded environment of the cluster, stars often come dangerously close to one another. When two stars collide or merge, they can form a single, more massive star. This process not only creates blue stragglers, but also explains why some stars in Omega Centauri are so much larger and brighter than expected. But stellar cannibalism isn't just about stars merging. In some cases, a larger star can strip material from a smaller companion, effectively consuming it over time. This process, known as mass transfer, can dramatically alter the properties of both stars involved. The larger star grows even more massive, while the smaller one is left as a faint, depleted remnant. These interactions are a testament to the dynamic and often violent nature of star clusters, where survival often depends on sheer size and strength. The study of Omega Centauri and its cannibalistic stars has profound implications for our understanding of stellar evolution and the life cycles of star clusters. By observing these interactions, astronomers can piece together the history of the cluster and the forces that have shaped it over billions of years. It also raises intriguing questions about the fate of other star clusters in the Milky Way. Could similar processes be at work elsewhere in the galaxy, or is Omega Centauri a unique case? The answers lie in continued observations and the development of new tools and techniques for studying these distant stellar communities. As we explore the mysteries of Omega Centauri, we're reminded that even in the vastness of space, survival often comes down to competition. The cannibalistic stars of this cluster are a stark reminder of the dynamic and ever-changing nature of the cosmos. Next, we'll turn our attention to another cosmic marvel, runaway stars, which have been ejected from their systems at incredible speeds, leaving behind a trail of questions about their origins and ultimate fate. Now, let's turn our gaze to a different kind of stellar phenomenon, runaway stars. These are stars that have been flung out of their systems at astonishing speeds, racing through the galaxy like cosmic outlaws. Unlike the cannibalistic stars of Omega Centauri, which thrive in crowded clusters, runaway stars are solitary travelers, hurtling through space at velocities that can exceed hundreds of kilometers per second. But how do stars achieve such incredible speeds, and what does their journey mean for the galaxy? The story of runaway stars begins with chaos. Most of these stars are thought to gain their extraordinary velocity through one of two dramatic events. The first is a close encounter with a supermassive black hole. When a star ventures too close to a black hole, the immense gravitational forces can slingshot it out of its original system, sending it careening across the galaxy. The second scenario involves the explosive death of a companion star in a binary system. When one star in a pair goes supernova, the sudden release of energy can propel the surviving star outward at incredible speeds, effectively ejecting it from its home. One of the most famous examples of a runaway star is Zeta Ophiuchi, a massive blue star racing through space at over 50 kilometers per second. Astronomers believe Zeta Ophiuchi was once part of a binary system. When its companion star exploded, the shockwave sent Zeta Ophiuchi hurtling away, leaving behind a glowing trail of interstellar gas. This star's journey is a vivid reminder of the explosive forces at play in the cosmos. But runaway stars aren't just fascinating cosmic anomalies, they also play a significant role in shaping the galaxy. As these stars travel, they interact with the interstellar medium, the gas and dust that fill the space between stars. Their high speeds create shock waves that can compress nearby gas, triggering the formation of new stars. In this way, runaway stars act as cosmic catalysts, seeding the galaxy with new stellar nurseries. Moreover, runaway stars can carry with them the remnants of their original systems, including planets or debris. This means that as they travel, they might spread elements forged in their former homes across vast distances, enriching different regions of the galaxy with heavy elements like carbon, oxygen, and iron. These elements are essential for the formation of planets and, ultimately, life. The study of runaway stars also provides valuable insights into the dynamics of stellar systems and the forces that govern them. By tracing the paths of these stars, astronomers can piece together the events that led to their ejection, shedding light on the violent processes that shape the galaxy. It's a reminder that even in the seemingly serene expanse of space, chaos and motion are ever present. As we follow the trails of these stellar wanderers, we're reminded of the galaxy's dynamic nature. Runaway stars are not just outliers, they are active participants in the ongoing story of the Milky Way. Next, we'll explore another cosmic marvel, a planet so extraordinary that it's believed to be made almost entirely of diamond. Now, let's shift our focus to a celestial gem unlike any other Pulsar J 1719-1438b, a planet that has captured the imagination of astronomers and dreamers alike. Known as the Diamond Planet, this extraordinary world is believed to be composed almost entirely of crystallized carbon, making it one of the most unique objects in the Milky Way. But how does a planet made of diamond come to exist, and what does its discovery mean for our understanding of planetary systems? The story of the Diamond Planet begins with a pulsar, a rapidly spinning neutron star that emits beams of radiation. Pulsar J 1719-1438b orbits this pulsar, completing a full revolution in just over 2 hours. This close proximity suggests that the planet was once part of a binary star system. Over time, the pulsar's intense gravitational pull stripped away the outer layers of its companion star, leaving behind a dense core composed primarily of carbon. Under extreme pressure, this carbon crystallized into diamond, transforming the remnant into a glittering, planet-sized jewel. The discovery of PSRJ 1719-1438b challenges our understanding of planetary formation. Unlike Earth or gas giants like Jupiter, this planet didn't form from a protoplanetary disk of dust and gas. Instead, it emerged from the remnants of a star, showcasing the incredible diversity of planetary systems in the galaxy. Its existence raises fascinating questions about the conditions required for such exotic worlds to form, and whether they might be more common than we once thought. The implications of the diamond planet extend beyond its dazzling composition. Studying this world provides valuable insights into the behavior of matter under extreme conditions. The intense pressure and temperature within the planet's core mimic those found in laboratory experiments aimed at understanding the properties of carbon and other elements. By observing PSRJ 1719-1438b, scientists can refine their models of planetary interiors and gain a deeper understanding of how materials behave in environments far beyond our own. Moreover, the diamond planet serves as a reminder of the galaxy's boundless creativity. It challenges us to rethink what a planet can be and opens the door to the possibility of other exotic worlds waiting to be discovered. Could there be planets made of other rare materials or even stranger compositions? The answer lies in the vast, uncharted reaches of the Milky Way. As we marvel at the brilliance of PSRJ 1719-1438b, we're reminded that the universe is full of surprises. This glittering world is not just a scientific curiosity. It's a testament to the endless variety of celestial objects that populate our galaxy. Next, we'll turn our attention to another mysterious object near the heart of the Milky Way. The enigmatic G2 cloud, a gas cloud that defied expectations by surviving a close encounter with the supermassive black hole at the galactic center. Now, let's venture closer to the heart of the Milky Way, where an enigmatic object has left astronomers both puzzled and intrigued: the mysterious G2 cloud. This peculiar gas cloud made headlines when it defied expectations by surviving a close encounter with Sagittarius, a star, the supermassive black hole at the center of our galaxy. What makes this cloud so unusual, and what does its survival tell us about the extreme environment near the galactic core? The G2 cloud was first detected in 2011, and its trajectory quickly revealed that it was on a collision course with Sagittarius, a star. Scientists initially predicted that the immense gravitational forces of the black hole would tear the cloud apart, consuming it entirely. However, as G2 approached its closest point in 2014, something unexpected happened: it survived. Instead of being devoured, the cloud stretched and distorted but remained intact, leaving researchers scrambling to explain its resilience. One leading theory suggests that the G2 cloud might not be a simple gas cloud at all. Some astronomers believe it could be hiding a star at its core, whose gravity helped hold the cloud together during its close encounter. This idea has sparked debates about the true nature of G2 and whether it represents a new class of objects in the galactic center. If a star is indeed present, it could explain how the cloud withstood the black hole's immense tidal forces, offering a fascinating glimpse into the complex dynamics at play near Sagittarius, a star. The survival of the G2 cloud also provides valuable insights into the behavior of matter in extreme environments. By studying how the cloud interacted with the black hole's gravitational field, scientists have gained a better understanding of the processes that govern accretion, the way black holes pull in and consume surrounding material. This knowledge is crucial for unraveling the mysteries of how supermassive black holes grow and influence their surroundings over time. Moreover, the G2 cloud's journey has shed light on the chaotic and dynamic nature of the galactic center. This region is a bustling hub of activity, with stars, gas clouds, and other objects constantly interacting under the influence of Sagittarius, a star's immense gravity. The cloud's unusual behavior highlights the complexity of these interactions and underscores the challenges of studying such a turbulent environment. As we continue to observe the G2 cloud, its story serves as a reminder of the surprises that await us in the Milky Way's core. It challenges our assumptions about how matter behaves near black holes and opens new avenues for exploring the extreme physics of the galactic center. Next, we'll turn our attention to another fascinating phenomenon: hypervelocity stars, which travel so fast they escape the Milky Way's gravity entirely. What propels these stars to such incredible speeds, and what can they tell us about the forces shaping our galaxy? Now, shifting our gaze to the outer reaches of the Milky Way, we encounter a phenomenon that defies the very fabric of our galaxy's gravitational hold: hypervelocity stars. These cosmic speedsters race through space at such incredible velocities that they break free from the Milky Way's gravitational grip, destined to drift into the vast emptiness of intergalactic space. But what could possibly propel a star to such extraordinary speeds, and where do these runaway stars come from? The story of hypervelocity stars begins at the heart of our galaxy, near the supermassive black hole Sagittarius, a star. Scientists believe that these stars are launched into their high-speed journeys through a process known as the slingshot effect. When a binary star system, a pair of stars orbiting each other, ventures too close to the black hole, the immense gravitational forces can tear the system apart. One star gets captured by the black hole, while the other is flung outward at an astonishing speed, sometimes exceeding 1 million miles per hour. This violent ejection transforms the star into a hypervelocity traveler, destined to leave the Milky Way behind. But not all hypervelocity stars originate from the galactic center. Some are thought to be the result of supernova explosions within binary systems. When one star in a pair explodes, the sudden release of energy can send its companion hurtling through space at breakneck speeds. Additionally, interactions with other massive objects, such as dense star clusters, can also accelerate stars to hypervelocity levels. These diverse origins highlight the dynamic and often chaotic nature of our galaxy, where gravitational encounters can dramatically alter the fate of stars. The study of hypervelocity stars offers valuable insights into the Milky Way's structure and history. By tracing their paths, astronomers can map the distribution of dark matter, the invisible substance that makes up much of the galaxy's mass. These stars also serve as cosmic probes, helping scientists understand the forces at play in extreme environments, from the intense gravity near black holes to the explosive power of supernova. As we watch these stars race toward the edges of the galaxy, they remind us of the incredible forces shaping the cosmos. Their journeys challenge our understanding of gravity and motion, while offering a glimpse into the Milky Way's turbulent past. Next, we'll explore another fascinating chapter in our galaxy's story: evidence of galactic cannibalism, where the Milky Way has consumed smaller galaxies to grow into the majestic spiral we see today. What remnants of these ancient collisions can we still find, and what do they reveal about our galaxy's evolution? Now, let's turn our attention to a dramatic chapter in the Milky Way's history, one that reveals its role as a cosmic predator. Over billions of years, our galaxy has grown not just by forming stars, but also by consuming smaller galaxies in a process known as galactic cannibalism. This violent yet fascinating phenomenon has left behind remnants that tell the story of the Milky Way's expansion and evolution. One of the most striking examples of this is the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy that has been slowly torn apart by the Milky Way's immense gravitational pull. Discovered in the 1990s, this dwarf galaxy is now little more than a stream of stars and gas, stretched across the sky in a long, faint arc. As it orbits the Milky Way, the Sagittarius dwarf is being gradually absorbed, its stars and material becoming part of our galaxy's structure. This ongoing process provides astronomers with a rare opportunity to study how larger galaxies grow by consuming their smaller neighbors. But the Sagittarius dwarf is not the only victim of the Milky Way's appetite. Other remnants of galactic cannibalism can be found in the form of stellar streams and clusters scattered throughout the galaxy. These streams are the torn-apart remains of ancient dwarf galaxies and star clusters, their stars now orbiting the Milky Way in elongated paths. By mapping these streams, scientists can trace the history of these mergers and understand how they have shaped the Milky Way's spiral arms, halo, and overall structure. Galactic cannibalism also plays a crucial role in enriching the Milky Way with new stars, gas, and even dark matter. When a smaller galaxy is absorbed, its stars and material are redistributed, contributing to the formation of new stars and influencing the dynamics of the galactic disk. This process has helped the Milky Way grow into the majestic spiral we see today, with its intricate arms and dense central bulge. The study of these remnants offers more than just a glimpse into the Milky Way's past. It also sheds light on the future of our galaxy. In about 4 billion years, the Milky Way is expected to collide with the Andromeda Galaxy, an event that will reshape both galaxies in a dramatic display of cosmic cannibalism. By understanding how the Milky Way has consumed smaller galaxies, we can better predict what might happen during this colossal merger. As we explore these remnants of galactic cannibalism, we uncover a story of growth, destruction, and renewal. The Milky Way's history is written in the stars it has absorbed, a testament to the dynamic and ever-changing nature of the cosmos. Next, we'll delve into another mysterious feature of our galaxy, the Fermi bubbles, massive structures of gamma rays that rise above and below the galactic plane. What secrets do these bubbles hold, and what do they reveal about the Milky Way's energetic past? Now, let's shift our gaze to one of the most enigmatic structures in the Milky Way, the Fermi bubbles. These colossal formations, stretching tens of thousands of light-years above and below the galactic plane, are like giant cosmic balloons filled with gamma rays. Discovered in 2010 by the Fermi Gamma Ray Space Telescope, these bubbles have puzzled astronomers ever since, offering a glimpse into the Milky Way's energetic and turbulent past. The Fermi bubbles are immense, each extending roughly 25,000 light-years from the galactic center. They glow with high-energy gamma rays, a type of radiation produced by some of the most extreme processes in the universe. But what could have created such massive structures? One leading theory suggests that they are the remnants of a massive outburst from the supermassive black hole at the heart of our galaxy, Sagittarius, a star. Millions of years ago, this black hole may have devoured an enormous amount of material, releasing a burst of energy so powerful that it sent shockwaves through the galaxy, carving out these bubbles in the process. Another possibility is that the bubbles were formed by a period of intense star formation near the galactic center. When massive stars are born and die in rapid succession, they can produce powerful stellar winds and supernova explosions, which might have collectively blown these bubbles into existence. Regardless of their exact origin, the Fermi bubbles are a testament to the dynamic and often violent processes that shape our galaxy. What makes these bubbles particularly fascinating is what they reveal about the Milky Way's history. The gamma rays they emit provide clues about the high-energy events that occurred in the galactic center long ago. By studying the bubbles, scientists can piece together a timeline of these events, helping us understand how the Milky Way has evolved over billions of years. The bubbles also serve as a reminder that our galaxy is not a static entity but a living, breathing system, constantly shaped by the forces within and around it. As we continue to explore the Fermi bubbles, we uncover more questions than answers. What triggered the event that created them? How do they interact with the rest of the galaxy? And what other secrets might they hold about the Milky Way's past? These questions drive astronomers to keep probing the depths of our galaxy, searching for clues that will help us unravel the mysteries of the cosmos. Next, we'll turn our attention to another invisible yet crucial component of the Milky Way, the mysterious dark matter halo that surrounds it, holding our galaxy together in its gravitational embrace. Now let's venture into the unseen, a mysterious force that shapes the very fabric of our galaxy. Surrounding the Milky Way is an invisible yet immensely powerful structure known as the dark matter halo. Unlike the stars, gas, and dust we can observe, this halo is made of dark matter, a substance that doesn't emit, absorb, or reflect light. Despite being invisible, its presence is undeniable as it exerts a gravitational pull that holds our galaxy together. The dark matter halo is like the hidden scaffolding of the Milky Way. Without it, the galaxy as we know it wouldn't exist. Stars and gas clouds orbit the galactic center at incredible speeds, and without the extra gravitational influence of dark matter, they would simply fly off into space. This invisible halo acts as a cosmic glue, binding everything together and maintaining the galaxy's structure over billions of years. But what exactly is dark matter? Scientists still don't have a definitive answer. It doesn't interact with light or ordinary matter in any way we can directly detect, making it one of the most elusive substances in the universe. What we do know is that it makes up about 85% of all matter in the cosmos. In the Milky Way, dark matter forms a vast spherical halo that extends far beyond the visible edges of the galaxy, enveloping everything within its gravitational grasp. Studying dark matter is no easy task. Since it doesn't interact with light, traditional telescopes are useless in detecting it. Instead, scientists rely on indirect methods, such as observing how its gravity affects the motion of stars and gas clouds. For example, stars on the outer edges of the galaxy move faster than they should if only visible matter were present. This discrepancy provides strong evidence for the existence of dark matter. Another approach involves studying gravitational lensing, a phenomenon where the gravity of dark matter bends the light from distant objects, distorting their appearance. By analyzing these distortions, astronomers can map the distribution of dark matter in the universe. Yet, despite these clever techniques, dark matter remains a profound mystery. Its true nature, whether it's made of undiscovered particles or something entirely different, is one of the biggest questions in modern astrophysics. The dark matter halo isn't just a passive observer in the galaxy's story. It plays an active role in shaping the Milky Way's evolution. For instance, it influences how galaxies form and grow, pulling in gas and dust that eventually collapse to form stars. It also affects the way galaxies interact with one another, as seen in the ongoing collision between the Milky Way and the Andromeda Galaxy, which is expected to occur in about 4 billion years. As we continue to explore the dark matter halo, we're reminded of how much of the universe remains hidden from our view. This invisible structure is a testament to the limits of our current understanding and the endless possibilities for discovery. Next, we'll turn our attention to another fascinating feature of the Milky Way, the galactic bar, a dense, elongated structure at the heart of our galaxy that plays a key role in its dynamics and star formation. Now, let's shift our gaze to the very heart of the Milky Way, where a dense and elongated structure known as the galactic bar takes center stage. This bar, stretching across thousands of light years, is a defining feature of our galaxy's core, shaping its dynamics and influencing the birth of new stars. The galactic bar is essentially a thick, elongated region of stars, gas, and dust that rotates around the galactic center. Unlike the spiral arms that extend outward, the bar is a more compact and rigid structure, acting as a kind of cosmic traffic controller for the material within the galaxy. Its gravitational pull directs the flow of gas and dust, funneling them toward the center and creating the conditions necessary for star formation. One of the most fascinating aspects of the galactic bar is its role in feeding the supermassive black hole at the Milky Way's core, Sagittarius, a star. As gas and dust are drawn inward by the bar's gravity, some of this material spirals toward the black hole, fueling its activity. This process not only sustains the black hole, but also triggers bursts of star formation in the surrounding regions, making the galactic bar a key player in the galaxy's life cycle. The bar's influence extends far beyond the galactic center. It also affects the motion of stars and gas throughout the Milky Way, creating ripples and waves that propagate through the galaxy. These gravitational interactions can compress gas clouds, leading to the formation of new stars and even entire star clusters. In this way, the galactic bar acts as a cosmic engine, driving the evolution of the Milky Way over billions of years. Interestingly, not all spiral galaxies have a central bar, but for those that do, like the Milky Way, it plays a crucial role in shaping their structure and behavior. Astronomers believe that bars may form as a natural consequence of galactic evolution, arising from the gravitational interactions between stars and gas within the galaxy. Over time, these interactions can cause the galaxy's disk to become unstable, leading to the formation of a bar-like structure. Studying the galactic bar has provided valuable insights into the Milky Way's history and future. For instance, simulations suggest that the bar's rotation may slow down over time, eventually transforming into a more spherical structure. This process could have profound implications for the galaxy's dynamics, altering the flow of gas and the rate of star formation in the central regions. As we continue to explore the galactic bar, we uncover more about the intricate dance of forces that shape our galaxy. From fueling star formation to influencing the motion of stars and gas, this central structure is a testament to the complexity and beauty of the Milky Way. Next, we'll turn our attention to another enigmatic object, magnetars, neutron stars with magnetic fields so powerful they defy imagination. Now, let's venture into the realm of the truly extraordinary magnetars, some of the most extreme and enigmatic objects in the Milky Way. These neutron stars are not just remnants of massive stellar explosions. They are cosmic powerhouses with magnetic fields so intense they defy comprehension. To put it into perspective, a magnetar's magnetic field is around 1,000 trillion times stronger than Earth's. If a magnetar were located halfway between the Earth and the Moon, its magnetic field would strip the information off every credit card on our planet. That's the kind of power we're talking about. Magnetars are born from the violent deaths of massive stars. When a star many times more massive than our Sun exhausts its fuel, it collapses under its own gravity and explodes in a supernova. What remains is a neutron star, a dense core packed with the mass of a star, but compressed into a sphere only about 12 miles across. In some cases, this neutron star is spinning rapidly and possesses an incredibly strong magnetic field, transforming it into a magnetar. These magnetic fields are so powerful that they can distort the very structure of atoms, creating conditions unlike anything else in the universe. But what makes magnetars truly fascinating and dangerous is their activity. These objects are known for releasing sudden, intense bursts of energy in the form of X-rays and gamma rays. These bursts, often called starquakes, occur when the magnetar's crust, under immense stress from its magnetic field, cracks and shifts. The energy released during these events can outshine the entire Milky Way for a fraction of a second. In fact, one of the most powerful gamma ray bursts ever detected, known as the soft gamma repeater, originated from a magnetar located about 50,000 light-years away. Even at that distance, it temporarily disrupted Earth's upper atmosphere. The dangers posed by magnetars don't stop there. If a magnetar were to erupt within a few light-years of Earth, the radiation could strip away our ozone layer, exposing the planet to harmful ultraviolet rays from the Sun. While the likelihood of such an event is extremely low, it underscores the sheer power of these objects. Magnetars also emit steady streams of X-rays and gamma rays, making their immediate surroundings uninhabitable for any form of life. Even spacecraft passing too close to a magnetar would be at risk of severe damage from its radiation. Despite their destructive potential, magnetars are invaluable to astronomers. Studying them provides insights into the behavior of matter under extreme conditions, offering clues about the fundamental forces that govern the universe. They also help us understand the life cycles of massive stars and the aftermath of supernova. By observing magnetars, scientists can piece together the story of how these cosmic powerhouses form and evolve. As we continue to explore the Milky Way, magnetars remind us of the galaxy's capacity for both beauty and danger. These enigmatic objects, with their unimaginable magnetic fields and explosive energy, are a testament to the extremes of nature. Next, we'll turn our attention to another mysterious stellar remnant, a ghostly neutron star that challenges our understanding of these cosmic phenomena. Now, let's shift our gaze to a cosmic enigma that challenges our understanding of stellar remnants, the ghostly neutron star. Unlike the magnetars we just explored, this neutron star stands out for a peculiar reason. It appears to have no visible companion. This solitary existence defies the expectations of astronomers, as most neutron stars are found in binary systems, orbiting another star or stellar remnant. So, what makes this ghostly neutron star so unusual, and what can it teach us about the life cycles of stars? Neutron stars, as we've seen, are the dense cores left behind after a massive star explodes in a supernova. Typically, these remnants are found in pairs orbiting another star or even another neutron star, but the ghostly neutron star breaks this pattern. It drifts alone through the galaxy, untethered to any visible companion. This raises a fascinating question. How did it end up so isolated? One possibility is that its companion star was destroyed during the supernova explosion, leaving the neutron star to wander the cosmos alone. Another theory suggests that the neutron star was ejected from its original system due to gravitational interactions, a cosmic game of billiards played out on a galactic scale. The formation of this ghostly neutron star offers a unique window into the chaotic aftermath of supernova. When a massive star explodes, the explosion is rarely symmetrical. The uneven distribution of energy can give the newborn neutron star a powerful kick, propelling it away from its original location at incredible speeds. In some cases, this kick is strong enough to eject the neutron star from its system entirely, leaving it to drift through the galaxy as a solitary wanderer. This process, known as a natal kick, is one of the key explanations for the existence of these ghostly neutron stars, but the mystery doesn't end there. The absence of a companion also makes this neutron star harder to detect. Without a nearby star to interact with, it emits less radiation, making it a faint and elusive object in the vastness of space. Yet, despite its ghostly nature, astronomers have managed to study it, revealing valuable insights into the behavior of neutron stars and the forces that shape their evolution. For instance, its isolation allows scientists to study the neutron star's intrinsic properties without the interference of a companion, providing a clearer picture of its magnetic field, rotation, and surface composition. What's truly remarkable is what this ghostly neutron star tells us about the diversity of stellar remnants. It challenges the assumption that neutron stars must always exist in pairs, reminding us that the universe is full of surprises. By studying these solitary wanderers, astronomers can refine their models of supernova explosions, stellar evolution, and the dynamics of binary systems. Each discovery brings us closer to understanding the complex and often unpredictable processes that govern the lives and deaths of stars. As we continue our journey through the Milky Way, the ghostly neutron star serves as a reminder of the galaxy's hidden mysteries. Its solitary existence is a testament to the chaotic and dynamic nature of the cosmos, where even the most well-understood phenomena can defy expectations. Next, we'll turn our attention to another ancient relic of the galaxy, the mysterious stars of the Milky Way's halo, which hold secrets from the dawn of the universe. Now, let's journey to the outer reaches of the Milky Way, where some of the oldest stars in the universe reside, the mysterious galactic halo stars. These ancient celestial bodies are not just old, they predate the formation of our galaxy itself, making them cosmic relics that hold secrets from the dawn of time. Scattered throughout the Milky Way's halo, a vast spherical region surrounding the galactic disk, these stars are like living fossils, offering a glimpse into the universe's earliest days. The origins of these halo stars are deeply tied to the chaotic beginnings of the Milky Way. Unlike the younger stars in the galactic disk, which formed from the dense gas and dust of the spiral arms, halo stars were born during a time when the universe was much younger and more turbulent. Many of these stars are thought to have formed in smaller, primordial galaxies that existed before the Milky Way as we know it today. Over billions of years, these smaller galaxies collided and merged, their stars becoming part of the Milky Way's halo. This process, known as galactic cannibalism, is how our galaxy grew to its current size, and why the halo is home to such ancient stars. What makes these stars truly fascinating is their composition. Unlike younger stars, which contain heavier elements forged in the hearts of previous generations of stars, halo stars are made almost entirely of hydrogen and helium, the simplest and oldest elements in the universe. This lack of heavier elements, or metals, as astronomers call them, tells us that these stars formed before the universe had time to produce and distribute these materials through supernova explosions. Studying their chemical makeup is like reading a cosmic history book, revealing the conditions of the early universe and the processes that shaped it. But the story of the halo stars doesn't end with their age and composition. Their distribution and motion also provide clues about the Milky Way's formation. Unlike the orderly, rotating stars in the galactic disk, halo stars move in random, chaotic orbits, a testament to their violent origins. Some even travel in the opposite direction to the galaxy's rotation, a clear sign that they were captured from other galaxies during mergers. By mapping their movements, astronomers can piece together the Milky Way's history, tracing the collisions and interactions that built our galaxy over billions of years. These ancient stars also challenge our understanding of star formation. In the early universe, the lack of heavy elements meant that stars could form in ways that are no longer possible today. Without the cooling effects of metals, the first stars were likely much larger and hotter than those we see now, burning brightly and dying quickly in spectacular supernova. The halo stars, while not the very first generation, are their close descendants, preserving the conditions of a time when the universe was young and untamed. As we study these ancient wanderers, we gain a deeper appreciation for the Milky Way's complex history. They remind us that our galaxy is not a static entity but a dynamic structure, shaped by countless collisions and mergers over billions of years. The halo stars are more than just relics, they are storytellers revealing the origins of the Milky Way and the universe itself. Next, we'll explore another cosmic oddity, the warped disk of our galaxy, a feature that defies the classic image of a flat, spiral galaxy and hints at the forces shaping its evolution. Now, let's turn our attention to a feature of the Milky Way that challenges our classic image of a flat, spiral galaxy, the galactic warp. Unlike the neat, flat disk we often imagine, the outer edges of our galaxy are twisted and bent, creating a shape that resembles a warped vinyl record. This peculiar distortion is not just a cosmic oddity, it's a clue to the forces shaping our galaxy's evolution. The Milky Way's warp is most noticeable in its outermost regions, where the disk of stars, gas, and dust curves upward on one side and downward on the other. This bending isn't random, it's the result of powerful forces at work. One leading theory suggests that the warp is caused by the gravitational pull of nearby satellite galaxies, such as the Large and Small Magellanic Cloud. As these smaller galaxies orbit the Milky Way, their gravity tugs on the outer edges of our galaxy's disk, distorting it over time. Another possibility is that the warp is driven by interactions with dark matter, the invisible substance that makes up most of the galaxy's mass. Dark matter's gravitational influence could be pulling the disk out of alignment, creating the warp we observe today. But the galactic warp isn't just a static feature, it's dynamic and ever-changing. Studies suggest that the warp actually moves around the galaxy, precessing like a spinning top. This motion adds another layer of complexity to our understanding of the Milky Way's structure. It also raises questions about how long the warp has existed and whether it will eventually flatten out or continue to evolve. The implications of the galactic warp extend far beyond its unusual shape. It provides valuable insights into the forces that shape galaxies over billions of years. By studying the warp, astronomers can learn more about the distribution of dark matter, the interactions between galaxies, and the processes that drive galactic evolution. It also challenges our assumptions about how galaxies form and maintain their structure, reminding us that the universe is far more dynamic and unpredictable than we often imagine. As we explore the Milky Way's warped disk, we're reminded that even the most familiar features of our galaxy can hold surprises. The warp is a testament to the complex interplay of forces that shape the cosmos, from the gravitational pull of neighboring galaxies to the mysterious influence of dark matter. Next, we'll uncover another cosmic mystery, a planet with clouds of metal vapor, a world so extreme it defies our understanding of planetary science. Now, shifting our gaze to a world that seems ripped straight out of science fiction, we encounter a planet so bizarre it defies our understanding of what's possible in the cosmos. Meet the strange exoplanet with metallic clouds, a place where the skies shimmer not with water vapor, but with vaporized metals like iron and titanium. This otherworldly discovery challenges everything we thought we knew about planetary atmospheres and the extremes of alien worlds. This exoplanet, known as WASP-121b, was first detected orbiting a star over 850 light-years away. What makes it truly extraordinary is its atmosphere, which is so hot that metals like iron and titanium exist not as solids or liquids but as gases. Imagine a world where the clouds aren't made of water droplets but of vaporized metal, creating a surreal, shimmering sky. The planet's surface temperature soars to over 2,000 degrees Celsius, making it one of the hottest exoplanets ever discovered. This extreme heat is due to its close orbit around its host star, which it circles in just over 1 day. The discovery of WASP-121b was made possible by advanced telescopes that can analyze the light passing through a planet's atmosphere. By studying the wavelengths of light absorbed by the planet, scientists detected the presence of metals in its atmosphere. This finding was groundbreaking because it revealed that planets can have atmospheres composed of elements we typically associate with solid or molten states, not gases. But what does this tell us about planetary science? For one, it shows that the universe is far more diverse and extreme than we ever imagined. Planets like WASP-121b push the boundaries of what we consider habitable or even survivable. They also provide a unique laboratory for studying how materials behave under extreme conditions, offering insights into the physics of high-temperature environments. Additionally, the presence of metallic clouds suggests that the processes shaping planetary atmospheres are far more complex than we once thought, involving not just chemistry but also extreme heat and pressure. The existence of such a planet also raises intriguing questions about the potential for other extreme worlds out there. Could there be planets with even stranger atmospheres, perhaps composed of elements we've yet to discover? Or could these metallic clouds play a role in the formation of new types of celestial bodies? As we continue to explore the cosmos, discoveries like WASP-121b remind us that the universe is full of surprises, waiting to challenge our assumptions and expand our understanding. As we marvel at this metallic marvel, we're reminded that the Milky Way is a treasure trove of cosmic oddities, each one offering a glimpse into the vast and varied tapestry of the universe. Next, we'll journey to the heart of our galaxy to explore its dense and mysterious central bulge, a region teeming with billions of stars and secrets waiting to be uncovered. Now, let's turn our attention to one of the most iconic features of our galaxy, the majestic spiral arms of the Milky Way, These sweeping arcs of stars, gas, and dust are not just beautiful to behold. They are the very engines of star formation, shaping the structure and evolution of our galaxy in profound ways. The Milky Way's spiral arms are like cosmic rivers, flowing with the raw materials needed to create new stars. These arms are regions of higher density, where gas and dust accumulate, creating the perfect conditions for star birth. As clouds of gas and dust compress under their own gravity, they ignite, giving rise to brilliant new stars and stellar nurseries. This process is ongoing, ensuring that the galaxy remains a vibrant, ever-changing tapestry of light and energy. But what gives the spiral arms their distinctive shape? The answer lies in a phenomenon known as density wave theory. Imagine the spiral arms as traffic jams in space, where stars and gas slow down as they move through these denser regions. This slowdown causes material to pile up, creating the bright, star-filled arms we observe. However, the stars themselves are not permanently bound to these arms. Instead, they move in and out of them over time, like cars merging into and out of a busy highway. The spiral arms also play a crucial role in the galaxy's evolution. By concentrating gas and dust, they act as catalysts for star formation, ensuring that the Milky Way continues to produce new generations of stars. These young, hot stars illuminate the arms, making them some of the most visible features of our galaxy. Over time, the energy and material released by these stars influence the surrounding environment, shaping the galaxy's structure and even triggering the formation of new spiral arms. Interestingly, the Milky Way is not alone in this spiral design. Many other galaxies in the universe share this structure, suggesting that spiral arms are a fundamental aspect of galactic evolution. Studying our own spiral arms provides valuable insights into how galaxies grow, change, and interact over billions of years. As we marvel at the beauty and complexity of the Milky Way's spiral arms, we're reminded of the dynamic nature of our galaxy. These arms are not static, they are alive with activity, constantly shaping and reshaping the cosmic landscape. Next, we'll venture into the heart of the Milky Way to explore its dense and mysterious central bulge, a region teeming with billions of stars and secrets waiting to be uncovered. Now, let's journey deeper into the heart of the Milky Way, where we encounter one of its most enigmatic features, the galactic bulge. This dense, bustling region at the center of our galaxy is a cosmic metropolis, home to billions of stars packed tightly together, creating a glowing hub of light and energy. Unlike the spiral arms we explored earlier, the bulge is a chaotic and crowded environment where stars orbit in all directions, forming a roughly spherical shape that stands out as the galaxy's central anchor. The formation of the galactic bulge is a story of cosmic collisions and gravitational forces. Scientists believe that the bulge formed early in the Milky Way's history as gas and dust accumulated at the galaxy's center, drawn in by the immense gravitational pull of the supermassive black hole Sagittarius, a star. Over time, this material condensed and ignited, giving birth to countless stars. Some theories suggest that the bulge may have also grown through mergers with smaller galaxies, their stars and gas adding to the dense core we see today. What makes the galactic bulge truly unique is its composition. Unlike the younger, hotter stars found in the spiral arms, the bulge is dominated by older, redder stars, some of which are among the oldest in the galaxy. These ancient stars provide a glimpse into the Milky Way's early days, offering clues about how galaxies form and evolve. The bulge is also rich in heavy elements, forged in the hearts of stars and scattered into space by supernova explosions. This abundance of elements has influenced the formation of new stars and planetary systems, shaping the galaxy's chemical makeup. But the galactic bulge is more than just a collection of stars. It's a dynamic region where extreme forces are at play. The intense gravitational field of Sagittarius, a star, influences the orbits of nearby stars, causing them to move at incredible speeds. Some stars whip around the black hole at millions of miles per hour, creating a frenetic dance of light and motion. This activity generates powerful radiation and magnetic fields, making the bulge a hotspot of cosmic energy. Studying the galactic bulge is no easy task. Its dense concentration of stars and thick clouds of dust obscure our view, making it difficult to observe directly. However, advances in infrared and radio astronomy have allowed scientists to peer through the veil, revealing the bulge's secrets. These observations have uncovered unexpected structures, such as bars of stars that stretch across the bulge, influencing the flow of gas and the formation of new stars. As we explore the galactic bulge, we're reminded of the Milky Way's complexity and the forces that shape its evolution. This central hub is not just a relic of the past, it's a vibrant, active region that continues to influence the galaxy's future. Next, we'll turn our attention to the rogue planets, those mysterious worlds that wander the galaxy without a star to call home, drifting through the cold, dark expanse of space. Now, let's venture into the shadowy outskirts of the Milky Way, where some of the most mysterious wanderers of the cosmos roam freely, the rogue planets. Unlike the planets we're familiar with, these celestial nomads don't orbit a star. Instead, they drift through the cold, dark expanse of space, untethered and alone. Imagine a world without a sunrise or sunset, where the only light comes from the faint glow of distant stars. These rogue planets are a fascinating enigma, challenging our understanding of planetary formation and survival in the harshest environments. The origins of rogue planets are as intriguing as their existence. Some scientists believe they were once part of a star system, born from the same swirling disk of gas and dust that forms planets around young stars. However, gravitational interactions with other planets or passing stars may have ejected them from their orbits, sending them hurtling into the void. Others suggest that rogue planets could have formed on their own, collapsing directly from clouds of gas and dust without ever being part of a star system. This second theory opens up the possibility that the galaxy is teeming with these solitary worlds, far more than we've yet discovered. Surviving in the cold depths of space is no small feat, but rogue planets have adapted in remarkable ways. Without the warmth of a nearby star, these planets are likely frozen and dark, with surface temperatures plunging to hundreds of degrees below zero. Yet, some may harbor hidden secrets beneath their icy exteriors. Scientists speculate that internal heat from radioactive decay or tidal forces could create subsurface oceans, potentially providing environments where life might exist. These hidden reservoirs of liquid water could make rogue planets unexpected candidates in the search for extraterrestrial life. Detecting rogue planets is a monumental challenge. Without the light of a star to illuminate them, they are nearly invisible to traditional telescopes. However, astronomers have developed clever techniques to spot these elusive worlds. One method involves gravitational microlensing, where the planet's gravity bends and magnifies the light from a distant star, creating a temporary brightening that reveals its presence. Another approach uses infrared telescopes to detect the faint heat signatures emitted by these cold, dark worlds. The discovery of rogue planets has profound implications for our understanding of the galaxy. They challenge the traditional view of planetary systems and suggest that the universe may be far more dynamic and unpredictable than we once thought. These wandering worlds also raise questions about the potential for life in the most unexpected places. Could a rogue planet drifting through the void harbor the building blocks of life in its hidden oceans? As we ponder the mysteries of rogue planets, we're reminded of the vastness and diversity of the Milky Way. These solitary wanderers are a testament to the galaxy's complexity, offering new insights into the processes that shape planetary systems and the potential for life beyond Earth. Next, we'll explore another fascinating phenomenon, the galactic fountain, where gas is ejected from the galactic disk and falls back in, creating a cosmic cycle of renewal. Now, let's turn our attention to a cosmic phenomenon that paints a vivid picture of the Milky Way's dynamic nature: the galactic fountain. Imagine a vast, invisible cycle where gas is ejected from the galactic disk, only to rain back down in a continuous loop of creation and renewal. This process, known as the galactic fountain, plays a crucial role in shaping the life cycle of our galaxy, influencing everything from star formation to the distribution of elements across the cosmos. The galactic fountain begins with the explosive energy of supernova, the dramatic deaths of massive stars. When a star reaches the end of its life and explodes, it sends shockwaves through the surrounding gas, propelling it outward at incredible speeds. This gas, now heated and energized, is launched high above the galactic disk, forming what astronomers call a galactic wind. These winds can carry gas thousands of light years into the halo, the sparse outer region of the galaxy. But the journey doesn't end there. Over time, the ejected gas begins to cool and condense, losing the energy that carried it outward. Gravity then takes over, pulling the gas back toward the galactic disk in a process often compared to rain falling from the sky. As the gas returns, it brings with it a wealth of heavy elements forged in the hearts of stars and scattered by supernova. This enriched material becomes the building blocks for new stars and planets, seeding the galaxy with the ingredients necessary for future generations of celestial objects. The galactic fountain isn't just a one-way process, it's a continuous cycle that helps regulate the galaxy's evolution. By redistributing gas and metals, it ensures that star formation doesn't occur in isolation. Instead, it creates a dynamic interplay between different regions of the galaxy, fostering a balance between creation and destruction. Without this process, the Milky Way might look very different, with star formation concentrated in isolated pockets rather than spread across the galactic disk. Studying the galactic fountain has also provided astronomers with valuable insights into the larger structure of the Milky Way. By observing the movement of gas in and out of the disk, scientists can map the galaxy's magnetic fields, trace the flow of cosmic material, and even uncover clues about the Milky Way's history. This phenomenon is a reminder that our galaxy is far from static. It's a living, breathing entity, constantly evolving through cycles of birth, death, and renewal. As we marvel at the galactic fountain, we're reminded of the intricate connections that bind the Milky Way together. This cosmic cycle not only shapes the galaxy's present but also lays the foundation for its future. Next, we'll dive into another mysterious aspect of our galaxy, the enigmatic galactic magnetic fields, which weave an invisible web of influence across the cosmos. Now, let's shift our gaze to an invisible force that quietly shapes the fabric of our galaxy, the mysterious galactic magnetic fields. These fields, though unseen, play a pivotal role in the Milky Way's structure and evolution, weaving an intricate web of influence across the cosmos. Galactic magnetic fields are vast, stretching across thousands of light years, and they are generated by the movement of charged particles, such as electrons and protons within the galaxy. These particles are set into motion by the rotation of the Milky Way, as well as by the explosive energy of supernova and the birth of new stars. Over time, this movement creates a complex network of magnetic lines that crisscross the galaxy, shaping the behavior of gas, dust, and even cosmic rays. One of the most fascinating roles of these magnetic fields is their influence on star formation. As clouds of gas and dust collapse under gravity to form new stars, the magnetic fields can either aid or hinder the process. In some cases, they provide support against gravitational collapse, slowing down star formation. In others, they channel gas into dense filaments, creating the perfect conditions for stars to ignite. This delicate balance ensures that star formation occurs at a steady pace, preventing the galaxy from burning through its fuel too quickly. But the influence of galactic magnetic fields doesn't stop there. They also play a crucial role in guiding cosmic rays, high-energy particles that travel through space at nearly the speed of light. These rays, which originate from supernova and other high-energy events, are deflected and redirected by the magnetic fields, creating intricate patterns of movement across the galaxy. Without these fields, cosmic rays would travel in straight lines, potentially causing havoc in regions where they accumulate. Instead, the magnetic fields act as a cosmic shield, distributing these particles more evenly and protecting the galaxy from their intense energy. Studying these magnetic fields is no easy task, as they are invisible to the naked eye and difficult to measure directly. Astronomers rely on indirect methods, such as observing the polarization of light from distant stars or mapping the alignment of dust grains, to piece together the structure and strength of these fields. What they've discovered is a dynamic and ever-changing system, one that evolves alongside the galaxy itself. The galactic magnetic fields are a testament to the hidden forces that govern the cosmos. They remind us that the Milky Way is not just a collection of stars and planets, but a complex, interconnected system where even the invisible plays a vital role. As we continue to unravel the mysteries of these fields, we gain a deeper understanding of how our galaxy functions and evolves. Next, we'll explore another fascinating feature of the Milky Way, the galactic superbubbles, massive cavities carved out by the explosive energy of supernova and their impact on the galaxy's structure. Now, let's turn our attention to one of the most dramatic features in the Milky Way, the galactic superbubbles. These colossal cavities, carved out by the explosive power of supernova, are like cosmic fingerprints left behind by the death of massive stars. Stretching hundreds of light years across, they reshape the interstellar medium, the vast sea of gas and dust that fills the space between stars, and play a crucial role in the galaxy's evolution. Superbubbles begin their story with the life and death of massive stars. When a star many times more massive than our Sun reaches the end of its life, it doesn't fade quietly, it explodes in a spectacular supernova. This explosion releases an enormous amount of energy, blasting shockwaves through the surrounding gas and dust. Over time, multiple supernovae occurring in the same region can combine their forces, creating a single, massive cavity known as a superbubble. These bubbles are not empty voids, though. They are filled with hot, ionized gas that glows brightly in X-rays and other wavelengths. The walls of the bubbles are made up of compressed gas and dust pushed outward by the force of the explosions. This compression can trigger the formation of new stars as the dense material along the edges collapses under its own gravity. In this way, superbubbles act as both destroyers and creators, tearing apart old structures while laying the groundwork for new ones. The impact of superbubbles extends far beyond their immediate surroundings. As they expand, they can break through the galactic disk, venting hot gas and heavy elements into the halo of the Milky Way. This process, known as galactic fountains, helps redistribute material across the galaxy, enriching the interstellar medium with elements forged in the hearts of stars. These elements, like carbon, oxygen, and iron, are essential building blocks for planets and even life itself. But superbubbles also have a more subtle influence on the galaxy. By clearing out large regions of gas and dust, they can alter the flow of cosmic rays and radiation, shaping the environment in which stars and planets form. They even play a role in regulating the rate of star formation, ensuring that the galaxy doesn't exhaust its fuel too quickly. Studying superbubbles is a challenge, as their immense size makes them difficult to observe in their entirety. Astronomers rely on a combination of X-ray, radio, and optical observations to piece together their structure and behavior. What they've found is a dynamic and ever-changing landscape, one that reflects the violent yet creative forces at work in the Milky Way. The galactic superbubbles are a reminder of the interconnectedness of the cosmos. They show us how the death of stars can give rise to new beginnings, and how the energy released in a single moment can shape the galaxy for millions of years to come. Next, we'll delve into the strange and enigmatic star clusters that defy classification, revealing yet another layer of the Milky Way's complexity. Now, shifting our gaze to another cosmic mystery, we encounter the strange star clusters scattered across the Milky Way. These clusters, unlike the more familiar open or globular clusters, defy easy classification, presenting astronomers with puzzles that challenge our understanding of stellar evolution. Star clusters are typically divided into two main types: open clusters, which are loose collections of young stars, and globular clusters, which are dense, spherical groups of ancient stars. But the strange star clusters we're focusing on today don't fit neatly into either category. They exhibit a mix of characteristics that blur the lines between these classifications, leaving scientists to wonder how they formed and what they can teach us about the galaxy's history. One of the most intriguing examples is the cluster known as Terzan 5, located near the galactic center. Unlike most globular clusters, which contain stars of roughly the same age, Terzan 5 hosts multiple generations of stars. This suggests that it formed over an extended period, possibly through a series of star-forming events rather than a single burst. The presence of younger stars alongside ancient ones hints at a complex and turbulent past, one that may have involved interactions with other clusters or even the Milky Way's central black hole. Another puzzling cluster is Palomar 12, which appears to have been captured by the Milky Way from a smaller, neighboring galaxy. Its stars are younger and more metal-rich than those in typical globular clusters, indicating that it originated in a different environment. This discovery raises questions about how many other clusters in the Milky Way might have been stolen from other galaxies, and what this means for our understanding of galactic evolution. These strange clusters also challenge our ideas about how stars form and evolve. In some cases, they contain stars with unusual chemical compositions, suggesting that they formed from gas clouds enriched by supernova or other cosmic events. This diversity provides a window into the conditions that existed in the early Milky Way, offering clues about how the galaxy's first stars and clusters came to be. Studying these enigmatic clusters is no easy task. Their unusual properties often require observations across multiple wavelengths, from visible light to infrared and radio. By piecing together these observations, astronomers can begin to unravel their origins and uncover the secrets they hold about the galaxy's past. What makes these clusters so fascinating is not just their strangeness, but what they reveal about the dynamic and ever-changing nature of the Milky Way. They remind us that the galaxy is not a static collection of stars, but a living, evolving system shaped by countless interactions and events. As we continue our journey through the Milky Way's mysteries, we'll next explore the dark lanes of dust that weave through the galaxy, obscuring our view and shaping the birth of new stars. Now, let's turn our attention to one of the most visually striking features of the Milky Way, the galactic dust lanes. These dark, winding ribbons of dust stretch across the galaxy, creating a dramatic contrast against the bright backdrop of stars. But these dust lanes are more than just a cosmic spectacle. They play a crucial role in the life cycle of the galaxy, shaping the birth of new stars and influencing how we observe the universe. Galactic dust lanes are composed of tiny particles of carbon, silicon, and other elements, often no larger than a grain of sand. These particles clump together to form vast clouds that can stretch for hundreds of light years. While they may seem like mere obstacles blocking our view, these dust clouds are actually the birthplaces of stars. Within their dense, cold interiors, gravity pulls the dust and gas together, eventually forming the seeds of new stars. Without these dusty nurseries, the Milky Way would be a far less vibrant place. However, the very dust that gives rise to stars also poses a challenge for astronomers. Dust absorbs and scatters visible light, making it difficult to observe objects behind it. This is why some regions of the Milky Way appear as dark voids in optical telescopes. To overcome this, scientists rely on other wavelengths of light, such as infrared and radio waves, which can penetrate the dust and reveal the hidden structures beyond. This multi-wavelength approach has allowed us to peer into the heart of star-forming regions like the Orion Nebula, uncovering the intricate processes at work. The dust lanes also play a role in shaping the galaxy's appearance. As they weave through the Milky Way's spiral arms, they create the dark bands that give the galaxy its distinctive mottled look. These lanes are not static, they are constantly shifting and evolving, influenced by the galaxy's rotation and the gravitational pull of nearby stars and gas clouds. This dynamic interplay between dust and gravity helps drive the ongoing cycle of star formation and destruction that defines the Milky Way. One of the most fascinating aspects of galactic dust is its ability to carry the building blocks of life. These particles often contain complex molecules, including organic compounds that are essential for life as we know it. When new stars and planets form within these dusty clouds, they inherit these molecules, potentially seeding the conditions for life to emerge. In this way, the dust lanes are not just cosmic roadblocks, they are also cosmic cradles nurturing the ingredients for future worlds. As we continue to study these enigmatic features, we gain a deeper understanding of how the Milky Way evolves over time. The dust lanes remind us that even the darkest corners of the galaxy hold the potential for creation and discovery. Next, we'll explore the high-speed winds that blow gas out of the galaxy, shaping its structure and influencing its future. Now, let's shift our gaze to a phenomenon that shapes the very fabric of the Milky Way, the mysterious galactic winds. These powerful, high-speed streams of gas surge outward from the galaxy, carrying with them the raw materials of stars and planets. But what drives these winds, and how do they influence the evolution of our galaxy? Let's dive in. Galactic winds are born in the most energetic regions of the Milky Way, often triggered by the explosive deaths of massive stars or the intense activity around supermassive black holes. When a star goes supernova, it releases an enormous amount of energy, propelling gas and dust outward at incredible speeds. Similarly, the supermassive black hole at the galaxy's center, Sagittarius, a star, can generate winds as it devours surrounding matter, heating the gas to extreme temperatures and sending it racing into space. These winds can reach speeds of millions of miles per hour, creating a cosmic exodus of material. But galactic winds are more than just a byproduct of stellar explosions and black hole activity. They play a crucial role in shaping the galaxy's future. As these winds sweep through the Milky Way, they carry away gas that could otherwise form new stars. This process, known as galactic feedback, helps regulate star formation, preventing the galaxy from burning through its fuel too quickly. Without these winds, the Milky Way might have exhausted its gas supply long ago, leaving it a dim and lifeless shadow of its current self. The impact of galactic winds extends far beyond the Milky Way. As they blow gas out of the galaxy, they enrich the surrounding intergalactic medium with heavy elements like carbon, oxygen, and iron. These elements, forged in the hearts of stars, are essential for the formation of planets and ultimately life. In this way, galactic winds act as cosmic couriers, delivering the building blocks of future worlds to the far reaches of the universe. Studying these winds is no easy task. Their immense speed and vast scale make them difficult to observe directly. However, astronomers have developed clever techniques to track their movement, using the light emitted by the gas to map its flow. By combining observations from telescopes across multiple wavelengths, scientists have begun to piece together the complex story of how these winds shape the galaxy. As we continue to unravel the mysteries of galactic winds, we gain a deeper appreciation for their role in the cosmic dance of creation and destruction. These winds remind us that the Milky Way is not a static entity but a dynamic, ever-changing system, driven by the forces of nature. Next, we'll explore the remnants of smaller galaxies torn apart by the Milky Way's gravity, shedding light on the galaxy's turbulent past. Now, let's turn our attention to the cosmic aftermath of the Milky Way's gravitational might, the galactic tidal streams. These ethereal ribbons of stars and gas are the remnants of smaller galaxies that ventured too close to our galaxy's immense gravitational pull, only to be torn apart in a celestial tug-of-war. These streams are more than just ghostly relics. They are key to understanding how the Milky Way has grown and evolved over billions of years. Galactic tidal streams form when a smaller galaxy or star cluster is drawn into the Milky Way's gravitational field. As it approaches, the intense tidal forces caused by the difference in gravity between the near and far sides of the smaller galaxy stretch and distort it, pulling stars and gas into long, flowing arcs. Over time, these arcs disperse, creating faint trails that wind through the galaxy's halo. These streams are often difficult to detect as they are made up of sparse, ancient stars that blend into the background of the Milky Way's brighter regions. Yet, their discovery has opened a window into the galaxy's violent past. One of the most famous examples of a galactic tidal stream is the Sagittarius dwarf spheroidal galaxy. Once a small but independent galaxy, it has been slowly devoured by the Milky Way over billions of years. Today, its remnants form a vast, looping stream of stars that wraps around our galaxy, a testament to the relentless power of gravity. By studying these streams, astronomers can trace the history of galactic mergers, piecing together how the Milky Way has grown by consuming its smaller neighbors. The significance of galactic tidal streams extends beyond their role as cosmic fossils. They provide crucial insights into the distribution of dark matter, the invisible substance that makes up most of the galaxy's mass. The way these streams are shaped and stretched reveals the gravitational influence of dark matter, helping scientists map its presence and understand its role in shaping the galaxy. Additionally, the stars within these streams often have unique chemical compositions, offering clues about the conditions in the early universe and the processes that formed the first galaxies. Detecting and studying these faint streams is a monumental challenge. Astronomers rely on advanced telescopes and sophisticated computer models to identify and map their intricate patterns. By combining observations from multiple wavelengths of light, they can trace the faint glow of ancient stars and reconstruct the paths of these streams across the sky. Each discovery adds another piece to the puzzle of the Milky Way's history, revealing a story of growth, destruction, and renewal. Galactic tidal streams remind us that the Milky Way is not just a collection of stars but a dynamic, evolving system shaped by its interactions with the cosmos. As we continue to explore these ghostly trails, we uncover the secrets of our galaxy's past and gain a deeper understanding of the forces that drive its evolution. Next, we'll delve into the mysterious gamma-ray sources scattered throughout the Milky Way, uncovering the energetic phenomena that light up our galaxy. Now, shifting our gaze to the enigmatic glow of the Milky Way, we encounter one of its most puzzling phenomena, the strange galactic gamma-ray sources. These bursts of high-energy radiation light up the galaxy, yet their origins remain shrouded in mystery. Unlike other cosmic events, these gamma-ray sources defy easy explanation, leaving astronomers both fascinated and perplexed. Gamma rays are the most energetic form of light in the universe, often produced by the most extreme and violent events, such as supernova, neutron star collisions, or the activity of supermassive black holes. However, the gamma-ray sources scattered throughout the Milky Way don't always fit neatly into these categories. Some appear to come from regions of space with no obvious stellar activity, while others flicker unpredictably, making them difficult to study. One leading theory suggests that these mysterious gamma-ray sources could be linked to pulsars, the rapidly spinning remnants of dead stars. Pulsars emit beams of radiation as they rotate, and under certain conditions, these beams might produce gamma rays. Another possibility is that they originate from dark matter particles colliding and annihilating each other, releasing bursts of energy in the process. While this idea is still speculative, it highlights the potential for these sources to unlock secrets about the invisible matter that permeates our galaxy. The significance of these gamma-ray sources extends beyond their mysterious origins. They serve as cosmic laboratories, allowing scientists to test theories about the behavior of matter and energy under extreme conditions. By studying their properties, astronomers can gain insights into the processes that shape the galaxy and the universe at large. Moreover, their unpredictable nature challenges our understanding of astrophysics, pushing researchers to develop new models and technologies to explain their behavior. Detecting and analyzing these gamma-ray sources is no small feat. Astronomers rely on specialized telescopes such as the Fermi Gamma-Ray Space Telescope to capture their fleeting signals. These instruments must sift through a sea of cosmic noise to pinpoint the faint, high-energy bursts that characterize these sources. Each discovery brings us closer to unraveling their secrets, offering a glimpse into the most energetic and elusive phenomena in the galaxy. As we continue to explore these strange gamma-ray sources, we are reminded of the Milky Way's capacity to surprise and challenge us. They are a testament to the galaxy's complexity, a reminder that even in our own cosmic backyard, there are mysteries waiting to be solved. Next, we'll journey to the heart of the Milky Way star-forming regions, where new stars are born in a dazzling display of cosmic creativity. Now, let's turn our attention to the bustling hubs of creation within the Milky Way, the galactic star factories. These regions, where stars are born in dazzling displays of cosmic energy, are some of the most vibrant and dynamic places in our galaxy. Among them, the Orion Nebula stands out as one of the most famous and well-studied examples. Located about 1,300 light-years from Earth, this stellar nursery is a hotbed of activity where clouds of gas and dust collapse under gravity to ignite the birth of new stars. The Orion Nebula is a prime example of how star formation works on a grand scale. Within its glowing clouds, pockets of gas become denser and denser until they reach a critical point, triggering nuclear fusion and giving birth to a star. This process doesn't happen in isolation. Entire clusters of stars can form simultaneously, creating a dazzling array of young, hot stars that light up the surrounding nebula. The intense radiation from these newborn stars ionizes the gas around them, producing the vibrant colors and intricate structures we see in images of the nebula. But the Orion Nebula is just one of many star-forming regions scattered throughout the Milky Way. These galactic star factories play a crucial role in the galaxy's life cycle. They are the engines of stellar evolution, producing the stars that will go on to shape the galaxy's future. Over millions of years, these stars will burn through their fuel, explode as supernova, and enrich the interstellar medium with heavy elements, which in turn become the building blocks for new stars and planets. It's a continuous cycle of creation and destruction that drives the evolution of the Milky Way. What makes these star factories so fascinating is their diversity. Some, like the Orion Nebula, are relatively close and easy to observe, while others lie hidden behind thick clouds of dust, visible only in infrared or radio wavelengths. Each region has its own unique characteristics, from the size and mass of the stars it produces to the conditions that trigger star formation. By studying these regions, astronomers can piece together the complex processes that govern how stars are born and how they influence their surroundings. The role of these star factories extends beyond just producing stars. They also shape the structure of the galaxy itself. The energy and radiation from young stars can push gas and dust outward, creating bubbles and voids in the interstellar medium. These structures can trigger further star formation in nearby regions, creating a ripple effect that spreads across the galaxy. In this way, star-forming regions are not just passive nurseries, they are active participants in the ongoing story of the Milky Way. As we marvel at the beauty and complexity of these galactic star factories, we are reminded of the Milky Way's incredible capacity for renewal and transformation. They are a testament to the galaxy's dynamic nature, where even the smallest processes can have far-reaching consequences. Next, we'll explore another mysterious aspect of our galaxy, the enigmatic sources of X-rays that defy explanation. Now, let's shift our gaze to one of the Milky Way's most puzzling phenomena, the mysterious galactic X-ray sources. These enigmatic objects emit intense bursts of X-rays, yet their origins remain shrouded in mystery. Unlike other cosmic phenomena, these sources don't fit neatly into any known category, leaving astronomers scratching their heads as they try to unravel their secrets. X-rays are a form of high-energy radiation, typically produced by some of the most extreme environments in the universe, such as black holes, neutron stars, and supernova remnants. However, the X-ray sources we're focusing on here don't seem to align with any of these familiar objects. They appear sporadically, sometimes flaring up with incredible intensity before fading back into obscurity. This unpredictable behavior makes them incredibly difficult to study and even harder to explain. One leading theory suggests that these mysterious X-ray sources could be linked to intermediate mass black holes, a class of black holes that are larger than stellar mass black holes but smaller than the supermassive ones found at the centers of galaxies. These elusive objects are thought to form through the merging of smaller black holes or the collapse of massive stars in dense star clusters. If they exist, they could be responsible for some of the unexplained X-ray emissions we observe. However, direct evidence of intermediate mass black holes remains scarce, leaving this theory in the realm of speculation. Another possibility is that these X-ray sources are the result of exotic stellar interactions. For example, some astronomers propose that they could be caused by white dwarfs or neutron stars undergoing unusual processes, such as sudden bursts of accretion or magnetic reconnection. These events could release vast amounts of energy in the form of X-rays, creating the mysterious signals we detect. Yet, even this explanation doesn't fully account for the diversity and unpredictability of these sources. What makes these X-ray sources so significant is their potential to reveal new aspects of astrophysics. By studying them, scientists hope to uncover new types of celestial objects or processes that challenge our current understanding of the universe. They could even provide clues about the nature of dark matter or the behavior of matter under extreme conditions. Every unexplained X-ray flare is a piece of the cosmic puzzle waiting to be deciphered. As we continue to explore the Milky Way, these mysterious X-ray sources remind us that there is still so much we don't know. They are a testament to the galaxy's endless capacity to surprise and intrigue us. Next, we'll venture into the shadowy realms of the Milky Way to uncover the secrets of its dark nebulae, where light itself seems to vanish. Now, let's step into the shadowy corners of the Milky Way, where light itself seems to disappear. These are the galactic dark nebulae, vast clouds of dust and gas so dense that they block the light from stars behind them, creating what appear to be voids in the night sky. But don't be fooled by their seemingly empty appearance. These dark nebulae are anything but lifeless. In fact, they are some of the most active and mysterious regions in our galaxy. Dark nebulae are composed primarily of tiny dust particles and cold molecular gas, which absorb and scatter visible light, making them opaque to our telescopes. This is why they appear as dark patches against the backdrop of brighter stars and glowing nebulae. One of the most famous examples is the Horsehead Nebula, a striking silhouette of dust and gas that has become an iconic image of cosmic beauty. But beyond their striking appearance, dark nebulae play a crucial role in the life cycle of stars. Within these dense clouds, the conditions are just right for star formation. The dust and gas in dark nebulae are so thick that they shield regions within them from external radiation, allowing temperatures to drop low enough for gravity to take over. Over time, these cold, dense pockets collapse under their own weight, forming protostars, the seeds of future stars. As these protostars gather more material, they ignite nuclear fusion, lighting up the surrounding gas and dust and often carving out glowing cavities within the dark nebula. In this way, dark nebulae are cosmic nurseries, giving birth to new stars and planetary systems. But the mysteries of dark nebulae don't end there. These regions are also home to complex molecules, including organic compounds like methanol and formaldehyde. Some scientists believe that the chemical processes occurring within dark nebulae could be the precursors to the building blocks of life. This raises fascinating questions about whether these shadowy clouds might hold clues to the origins of life in the universe. Despite their importance, dark nebulae remain challenging to study. Their very nature blocking light makes them difficult to observe directly. Astronomers rely on infrared and radio telescopes to peer through the dust and uncover the secrets hidden within. These observations have revealed intricate structures, turbulent motions, and even the presence of young stars still embedded in their birth clouds. Dark nebulae remind us that even in the darkest corners of the galaxy, there is activity and potential. They are a testament to the dynamic and ever-changing nature of the Milky Way, where even the absence of light can lead to the birth of something extraordinary. Next, we'll explore the strange galactic radio sources, where invisible signals from the depths of space hold their own set of cosmic mysteries. Now, let's tune into the invisible symphony of the Milky Way, where strange and mysterious radio signals echo through the vastness of space. These are the galactic radio sources, invisible to the naked eye but detectable through the power of radio telescopes. Unlike the light we see, these radio waves reveal a hidden layer of the galaxy, uncovering phenomena that defy our expectations and challenge our understanding of the cosmos. Galactic radio sources come in many forms, each with its own unique story. Some are the remnants of massive stars that ended their lives in spectacular supernova explosions, leaving behind pulsars rapidly spinning neutron stars that emit beams of radio waves like cosmic lighthouses. Others are the result of supermassive black holes at the centers of galaxies, including our own, which spew out jets of particles at nearly the speed of light, creating intense radio emissions. And then there are the enigmatic sources that seem to have no clear explanation, their origins shrouded in mystery. One of the most fascinating examples is Sagittarius, a star, the supermassive black hole at the heart of the Milky Way. While it's relatively quiet compared to other galactic centers, it occasionally flares up, emitting bursts of radio waves that hint at the chaotic environment surrounding it. These flares provide valuable clues about the behavior of black holes and the extreme conditions near the galactic center, but not all radio sources are tied to such dramatic events. Some are the result of more subtle processes, like the interaction of cosmic rays with magnetic fields or the slow, steady emission from clouds of ionized gas. These quieter sources may not grab headlines, but they play a crucial role in shaping the galaxy's structure and evolution. For instance, the Fermi bubbles, massive structures of gamma rays and radio waves extending above and below the galactic plane, are thought to be the remnants of an ancient outburst from the Milky Way's central black hole. They serve as a reminder of the galaxy's dynamic and sometimes violent past. What makes these radio sources truly strange is their unpredictability. Some, like fast radio bursts, appear suddenly and vanish just as quickly, leaving astronomers scrambling to understand their origins. Others, like the mysterious radio filaments near the galactic center, stretch for light years and seem to defy conventional explanations. These filaments, discovered in the 1980s, are long, thin structures that emit radio waves, but their exact nature remains a puzzle. Are they the result of magnetic fields, cosmic winds, or something entirely new? The answers could reshape our understanding of the galaxy. Studying these radio sources is no easy task. Radio telescopes must sift through a sea of signals, separating the faint whispers of distant phenomena from the noise of Earth-based interference. Yet, the effort is worth it. Each discovery brings us closer to unraveling the secrets of the Milky Way, from the behavior of black holes to the birth and death of stars. As we continue to explore these strange galactic radio sources, one thing becomes clear: the Milky Way is far more complex and dynamic than we ever imagined. These invisible signals are a reminder that there is still so much to learn about our galaxy, and that the universe is full of surprises waiting to be uncovered. Next, we'll turn our attention to the galactic star streams, where the remnants of ancient collisions paint a picture of the Milky Way's turbulent history. Now, let's shift our gaze to the cosmic rivers of stars that flow through the Milky Way galactic star streams. These delicate ribbons of light are the remnants of smaller galaxies that were torn apart by the immense gravitational pull of our own galaxy. They are like ghostly fingerprints, marking the Milky Way's history of galactic cannibalism and revealing the violent yet beautiful process of galactic mergers. Galactic star streams are formed when a smaller galaxy ventures too close to the Milky Way. Over time, the gravitational forces of our galaxy stretch and pull the smaller one apart, scattering its stars into long, flowing streams that orbit the galactic center. These streams can stretch for thousands of light years, weaving through the Milky Way like cosmic threads. One of the most famous examples is the Sagittarius dwarf spheroidal galaxy, which has been slowly devoured by the Milky Way over billions of years. Its stars now form a vast, looping stream that wraps around our galaxy, a testament to the relentless pull of gravity. But why are these star streams so important? They serve as a cosmic record, preserving the history of the Milky Way's growth and evolution. By studying the composition, motion, and distribution of stars within these streams, astronomers can piece together the story of how our galaxy came to be. For instance, the stars in these streams often retain the chemical signatures of their original galaxies, providing clues about the conditions in those smaller systems before they were consumed. This information helps scientists understand not only the Milky Way's past, but also the broader processes that shape galaxies across the universe. One of the most intriguing aspects of galactic star streams is their role in revealing the distribution of dark matter. As these streams are pulled apart, their shapes and movements are influenced by the invisible dark matter that permeates the Milky Way. By mapping the streams, astronomers can infer the distribution and density of dark matter, shedding light on one of the greatest mysteries in modern astrophysics. In this way, star streams act as cosmic probes, helping us explore the unseen forces that govern the universe. The study of galactic star streams also highlights the dynamic nature of the cosmos. Galaxies are not static islands of stars, but ever-changing systems that grow and evolve through collisions and mergers. These streams remind us that the Milky Way is still growing, slowly incorporating smaller galaxies into its structure. Over time, these mergers will continue to shape our galaxy, influencing its structure, star formation, and even the fate of its central black hole. As we trace the paths of these star streams, we gain a deeper appreciation for the interconnectedness of the universe. They are not just remnants of destruction, but also symbols of creation, as the merging of galaxies fuels the birth of new stars and planetary systems. Each stream tells a story of cosmic transformation, a reminder that even in the vastness of space, nothing remains unchanged. Next, we'll turn our attention to the mysterious galactic infrared sources, where invisible light reveals hidden wonders in the Milky Way. Now, let's step into the hidden world of the Milky Way, where light invisible to our eyes reveals some of the galaxy's most enigmatic secrets, the mysterious galactic infrared sources. These are regions or objects that emit intense infrared radiation, a type of light that lies just beyond the red end of the visible spectrum. While we can't see this light with our naked eyes, telescopes equipped with infrared detectors have unveiled a universe teeming with activity that would otherwise remain hidden. Infrared radiation is often emitted by objects that are too cool, too dusty, or too distant to shine brightly in visible light. This makes it a powerful tool for uncovering the hidden corners of the Milky Way. Some of these infrared sources are well understood, like newborn stars shrouded in thick clouds of dust or the remnants of dying stars, but others defy explanation, glowing brightly in infrared without any obvious cause. These mysterious sources have puzzled astronomers for decades, sparking debates about their origins and significance. One leading theory suggests that some of these infrared sources could be young, massive stars still in the process of forming. These stars are often buried deep within dense clouds of gas and dust, which absorb their visible light but allow infrared radiation to escape. Another possibility is that these sources are the remnants of supernova exploded stars, whose debris is still glowing with residual heat. In some cases, they might even be distant galaxies whose light has been stretched into the infrared by the expansion of the universe. But not all infrared sources fit neatly into these categories. Some appear to be isolated, with no visible stars or galaxies nearby to explain their emissions. These enigmatic objects have led scientists to consider more exotic explanations, such as the presence of hidden black holes or even entirely new types of celestial phenomena. The mystery deepens when we consider that some of these sources flicker or change brightness over time, suggesting dynamic processes at work that we don't yet fully understand. The significance of these infrared sources extends far beyond their mystery. They provide a unique window into the processes that shape our galaxy, from the birth of stars to the violent deaths of massive ones. By studying them, astronomers can learn more about the life cycles of stars, the distribution of dust and gas in the Milky Way, and even the role of dark matter in shaping galactic structures. Infrared observations also help us peer through the dense clouds that obscure the galactic center, revealing the bustling activity near the supermassive black hole at the heart of our galaxy. As we continue to explore these infrared sources, we're reminded that the Milky Way is full of surprises. Even in the light we cannot see, there are stories waiting to be uncovered, stories of creation, destruction, and the endless dance of cosmic forces. These mysterious sources challenge our understanding of the universe, pushing us to ask new questions and seek new answers. Next, we'll journey to the remnants of exploded stars, where the echoes of stellar death shape the future of the galaxy. Now, let's turn our attention to the dramatic aftermath of stellar explosions, the galactic supernova remnants. These are the cosmic echoes of stars that have met their fiery end, leaving behind a legacy that shapes the very fabric of the Milky Way. When a massive star exhausts its fuel, it doesn't fade quietly into the night. Instead, it explodes in a spectacular supernova, releasing an immense amount of energy and scattering its material across space. What remains is a supernova remnant, a glowing shell of gas and dust that tells the story of the star's final moments. Supernova remnants are more than just beautiful cosmic phenomena. They play a crucial role in the life cycle of the galaxy. As the shockwaves from the explosion ripple through space, they sweep up surrounding gas and dust, compressing it and triggering the formation of new stars. This process is like a cosmic recycling program where the death of one star gives birth to countless others. The remnants also enrich the interstellar medium, the vast expanse of gas and dust between stars, with heavy elements forged in the heart of the exploding star. Elements like iron, gold, and even the calcium in your bones were created in these stellar explosions and scattered across the galaxy. One of the most famous supernova remnants is the Crab Nebula, the result of a supernova observed by astronomers in the year 1054. Today, it's a swirling cloud of gas and dust, illuminated by the energy of a pulsar at its core. But not all remnants are as well known or as easily visible. Some are hidden within dense clouds of dust, detectable only through their radio or X-ray emissions. Others, like the Vela supernova remnant, stretch across vast regions of space, their delicate filaments glowing with the light of ionized gas. The study of supernova remnants provides valuable insights into the processes that drive stellar evolution and galactic dynamics. By analyzing their structure and composition, astronomers can piece together the conditions that led to the explosion and understand how these events influence their surroundings. For example, the shock waves from supernova can trigger the collapse of nearby gas clouds, setting the stage for new star formation. At the same time, the heavy elements they release become the building blocks for planets and ultimately life. But supernova remnants are not just relics of the past. They are active participants in the ongoing story of the Milky Way. Their energy heats the interstellar medium, their shockwaves shape the galaxy's structure, and their material fuels the next generation of stars and planets. In this way, the death of a star becomes a catalyst for new beginnings, a reminder that even in destruction there is creation. As we continue to explore these remnants, we uncover not just the history of individual stars, but the interconnected processes that shape the galaxy as a whole. Next, we'll delve into the strange and fascinating world of binary star systems, where two stars orbit each other in a delicate cosmic dance. Now, let's shift our gaze to the intriguing world of binary star systems, where two stars orbit each other in a delicate cosmic dance. These systems are far from ordinary. Some exhibit properties so unusual that they challenge our understanding of stellar evolution. Binary stars are incredibly common in the Milky Way, with nearly half of all stars having a companion. But among these, there are systems that stand out for their peculiar behaviors and unique characteristics. Take, for example, the case of contact binaries, where two stars orbit so closely that they share a common atmosphere. These stars are literally touching, their outer layers mingling in a swirling embrace. This extreme proximity can lead to dramatic interactions, such as mass transfer, where one star siphons material from its companion. Over time, this process can alter the star's evolution, sometimes leading to explosive outcomes like nova or even supernova. Another fascinating example is the X-ray binaries, where one of the stars is a compact object, a neutron star or a black hole. As the companion star orbits, its material is pulled toward the compact object, forming a glowing accretion disk. The intense gravitational forces heat the material to millions of degrees, causing it to emit powerful X-rays. These systems are like cosmic laboratories, offering insights into the behavior of matter under extreme conditions and the nature of compact objects themselves. Then there are the eclipsing binaries, where the stars periodically pass in front of each other from our perspective on Earth. This alignment causes their combined light to dim and brighten in a predictable pattern, allowing astronomers to study their properties in remarkable detail. By analyzing these light curves, scientists can determine the stars' sizes, masses, and even their atmospheres, providing a wealth of information about stellar structure and evolution. But perhaps the most mysterious are the runaway binaries, where the two stars are hurtling through space at incredible speeds. These systems are thought to have been ejected from their birthplaces by the gravitational kick of a nearby supernova or a close encounter with another star. Their high velocities make them outliers in the galaxy, and studying them can reveal clues about the chaotic environments where they originated. Binary star systems are more than just curiosities. They are key to understanding the life cycles of stars. They provide a natural laboratory for testing theories of stellar evolution, from the birth of stars in dense molecular clouds to their eventual deaths as white dwarfs, neutron stars, or black holes. By studying these systems, astronomers can piece together the complex processes that shape the stars and, by extension, the galaxy itself. As we continue our journey through the Milky Way, we'll next explore the eerie regions known as galactic star graveyards, where the remnants of dead stars gather in silent testament to the galaxy's turbulent history. Now, let's venture into the hauntingly beautiful regions of the Milky Way known as galactic star graveyards. These are the final resting places of stars that have burned through their fuel and reached the end of their life cycles. Here, the remnants of once bright stars, white dwarfs, neutron stars, and even black holes gather in eerie silence, offering a glimpse into the galaxy's ancient past and the fate that awaits many of its stellar inhabitants. White dwarfs, the dense cores left behind after a star like our Sun exhausts its nuclear fuel, are among the most common residents of these graveyards. Though no longer producing energy through fusion, these stellar corpses glow faintly with residual heat, slowly cooling over billions of years. They are incredibly dense, packing a mass comparable to the Sun into a sphere roughly the size of Earth. Studying white dwarfs helps astronomers understand the final stages of stellar evolution for stars of similar mass, as well as the processes that govern their cooling and eventual fading into darkness. Neutron stars, on the other hand, are the remnants of massive stars that ended their lives in spectacular supernova explosions. These incredibly dense objects are composed almost entirely of neutrons, with a teaspoon of neutron star material weighing as much as a mountain on Earth. Some neutron stars, known as pulsars, emit beams of radiation that sweep across space like cosmic lighthouses, providing valuable data about their structure and the extreme conditions within them. Others, called magnetars, possess magnetic fields trillions of times stronger than Earth's, making them some of the most powerful magnetic objects in the universe. In the darkest corners of these graveyards, black holes lurk, regions of space where gravity is so intense that not even light can escape. These enigmatic objects are the final remnants of the most massive stars, and their presence in star graveyards serves as a stark reminder of the violent processes that shape the galaxy. By studying black holes, scientists can explore the limits of our understanding of gravity and the behavior of matter under the most extreme conditions. Galactic star graveyards are more than just collections of dead stars. They are archives of the Milky Way's history. The distribution and properties of these remnants reveal clues about the galaxy's formation, the types of stars that once populated it, and the dynamic processes that have shaped its evolution over billions of years. They also provide a window into the future, showing us what will eventually happen to many of the stars we see today. As we move forward in our exploration of the Milky Way's mysteries, we'll next turn our attention to the enigmatic gamma-ray bursts that occasionally light up the galaxy, offering fleeting but powerful insights into some of the most energetic events in the universe. Now, let's shift our gaze to one of the most explosive and mysterious phenomena in the Milky Way gamma-ray bursts. These fleeting but incredibly powerful events are among the most energetic occurrences in the universe, capable of releasing more energy in a few seconds than our Sun will emit over its entire lifetime. While most gamma-ray bursts are observed in distant galaxies, some originate within our own Milky Way, offering scientists a closer look at these cosmic fireworks. Gamma-ray bursts are thought to arise from two main sources. The first occurs when a massive star, many times heavier than our Sun, exhausts its nuclear fuel and collapses under its own gravity, triggering a supernova explosion. In some cases, this collapse leads to the formation of a black hole, and as matter spirals into it, intense jets of gamma rays are ejected at nearly the speed of light. These jets, if pointed toward Earth, produce the bright flashes we detect as gamma-ray bursts. The second source involves the collision of two neutron stars, which releases a tremendous amount of energy in the form of gamma rays and gravitational waves. These mergers are rare but provide critical insights into the behavior of matter under extreme conditions. The dangers posed by gamma-ray bursts are not to be underestimated. If one were to occur relatively close to Earth within a few thousand light years, it could have catastrophic effects. The intense radiation could strip away the ozone layer, exposing the planet to harmful ultraviolet rays from the Sun and potentially triggering mass extinctions. Fortunately, the likelihood of such an event is extremely low, as gamma-ray bursts are rare and typically occur far from our solar system. Still, their existence serves as a reminder of the dynamic and sometimes violent nature of our galaxy. Scientists continue to study these bursts to better understand their origins and the mechanisms that drive them. By analyzing the light and radiation emitted during these events, researchers can piece together the conditions that lead to such extreme phenomena. Gamma-ray bursts also provide a unique opportunity to study the early universe, as their light can travel billions of light years, offering a glimpse into the distant past. As we continue our journey through the Milky Way's strange and wondrous objects, we'll next explore the vibrant regions where new stars are born, the galactic star nurseries. These cosmic cradles are teeming with activity, shaping the future of our galaxy one star at a time. Now, let's turn our attention to the cosmic cradles of the Milky Way, the galactic star nurseries. These vibrant regions are where the magic of star formation unfolds, creating the building blocks of our galaxy. Among the most famous of these nurseries is the Eagle Nebula, a stunning cloud of gas and dust that has become an iconic symbol of stellar birth. Within these nurseries, gravity pulls together vast clouds of hydrogen gas, compressing them until the pressure and temperature become so intense that nuclear fusion ignites, giving birth to a new star. Star nurseries are not just beautiful to observe, they play a crucial role in the life cycle of the Milky Way. As stars form, they light up their surroundings, ionizing the gas around them and creating glowing regions known as H2 regions. These areas become hotspots of activity where young stars interact with their environment, shaping the nebula and triggering further star formation. Over time, these nurseries contribute to the galaxy's structure, enriching it with new stars and the heavy elements forged in their cores. One of the most fascinating aspects of star nurseries is their diversity. Some, like the Orion Nebula, are bustling with activity, producing dozens of stars at once. Others, like the dark and quiet Bok globules, are more isolated, forming stars in solitude. Each nursery tells a unique story about the conditions that lead to star formation, offering astronomers a glimpse into the processes that shape our galaxy. The life cycle of a star nursery doesn't end with the birth of stars. As these young stars grow, their intense radiation and stellar winds begin to blow away the surrounding gas and dust, dispersing the nursery and revealing the newly formed stars. This process, known as feedback, can trigger new waves of star formation in nearby regions, creating a ripple effect that influences the galaxy's evolution. As we marvel at these cosmic cradles, it's worth noting that star nurseries are not just distant phenomena, they are part of our galactic neighborhood. The Milky Way is home to countless such regions, each contributing to the ongoing story of our galaxy. From the Eagle Nebula to the Orion Nebula, these nurseries remind us that the universe is a place of constant creation and renewal. With this glimpse into the birthplaces of stars, we'll next explore the strange and enigmatic pulsars that dot the Milky Way, offering a window into the extreme physics of neutron stars. These cosmic lighthouses are as mysterious as they are fascinating, and their stories are waiting to be told. Now, shifting our gaze to the cosmic lighthouses of the Milky Way, we encounter the strange and enigmatic galactic pulsars. These rapidly spinning neutron stars are among the most extreme objects in the universe, emitting beams of radiation that sweep across space like the light from a lighthouse. But not all pulsars are created equal. Some exhibit bizarre and unpredictable behaviors that challenge our understanding of these dense stellar remnants. One of the most intriguing types of pulsars is the intermittent pulsar. Unlike their more consistent counterparts, these pulsars switch on and off, sometimes disappearing for days, months, or even years before suddenly reappearing. This erratic behavior has puzzled astronomers who are still working to uncover the mechanisms behind these mysterious pauses. One theory suggests that changes in the pulsar's magnetic field or the flow of charged particles around it could be responsible, but the true cause remains a cosmic mystery. Pulsars are born from the explosive deaths of massive stars in supernova. When a star exhausts its nuclear fuel, its core collapses under gravity, forming a neutron star, a city-sized object with the mass of a sun. If this neutron star is highly magnetized and spinning rapidly, it becomes a pulsar, emitting beams of radiation from its magnetic poles. These beams are detected as regular pulses of light, radio waves, or even X-rays as the pulsar rotates. The study of pulsars, especially those with unusual properties, has provided invaluable insights into the physics of neutron stars. For instance, intermittent pulsars help us understand how these objects evolve over time and how their magnetic fields interact with their surroundings. They also serve as natural laboratories for testing the laws of physics under extreme conditions, such as intense gravity and magnetic fields billions of times stronger than Earth. Beyond their scientific value, pulsars have practical applications as well. Their precise pulses make them excellent cosmic clocks, used by astronomers to measure distances in space and even detect gravitational waves. Some pulsars, known as millisecond pulsars, spin hundreds of times per second, offering a level of precision that rivals the best atomic clocks on Earth. As we continue to unravel the secrets of these strange galactic pulsars, we gain a deeper appreciation for the dynamic and ever-changing nature of the Milky Way. From their explosive origins to their unpredictable behaviors, pulsars remind us that the universe is full of surprises waiting to be discovered. Next, we'll delve into the mysterious clumps of dark matter scattered throughout the Milky Way, exploring how these invisible structures shape the galaxy we call home. Now, as we venture deeper into the unseen fabric of the Milky Way, we encounter one of the most elusive and mysterious components of our galaxy, the clumps of dark matter. Unlike the stars, gas, and dust that light up the night sky, dark matter is invisible, detectable only through its gravitational effects on the visible universe. These clumps scattered throughout the galaxy play a crucial role in shaping the Milky Way structure and evolution. Dark matter makes up about 85% of the universe's total mass, yet it neither emits nor absorbs light, making it impossible to observe directly. So, how do we know it's there? Astronomers detect dark matter clumps by observing their gravitational influence on visible matter. For example, stars and gas clouds orbiting the Milky Way move in ways that can only be explained by the presence of unseen mass. These movements reveal the hidden hand of dark matter, pulling and shaping the galaxy from the shadows. One of the most compelling pieces of evidence for dark matter clumps comes from gravitational lensing. When light from distant galaxies passes near a dark matter clump, its path is bent, creating distorted or magnified images of the background galaxy. This phenomenon allows astronomers to map the distribution of dark matter, revealing its clumpy nature. These clumps vary in size from small, dense regions to vast, diffuse clouds, each contributing to the galaxy's overall gravitational framework. The significance of these dark matter clumps extends far beyond their gravitational effects. They are thought to act as cosmic scaffolding, providing the framework around which galaxies form and grow. Without dark matter, the Milky Way as we know it might never have come into existence. Its gravitational pull helped gather gas and dust in the early universe, triggering the birth of stars and the formation of galactic structures. But the mystery of dark matter doesn't end there. Scientists are still working to understand its true nature. Is it made of exotic particles that interact only through gravity, or does it have properties we have yet to discover? The clumps within the Milky Way offer a unique opportunity to study dark matter up close, providing clues that could unlock one of the greatest puzzles in modern astrophysics. As we continue to explore these invisible structures, we gain a deeper understanding of the forces that shape our galaxy. Dark matter clumps remind us that much of the universe remains hidden, waiting to be uncovered. Next, we'll turn our attention to the enigmatic microquasars, small but powerful objects that mimic the behavior of their larger, more distant cousins. Now, shifting our gaze to the smaller yet equally fascinating phenomena within the Milky Way, we encounter the enigmatic microquasars. These cosmic objects are essentially miniature versions of quasars, the incredibly bright and distant powerhouses found at the centers of galaxies. But what makes microquasars so intriguing is their compact size and their ability to mimic the behavior of their larger counterparts on a much smaller scale. Microquasars are formed when a black hole or neutron star pulls material from a nearby companion star. As this material spirals inward, it forms a swirling disk of superheated gas known as an accretion disk. The intense gravitational forces at play generate enormous amounts of energy, causing the disk to emit powerful jets of particles that travel at nearly the speed of light. These jets, which can extend for light years, are a hallmark of microquasars and make them some of the most dynamic objects in our galaxy. What makes microquasars particularly valuable to astronomers is their ability to act as cosmic laboratories. By studying these smaller scale systems, scientists can gain insights into the behavior of supermassive black holes and quasars, which are too distant and complex to observe in detail. Microquasars provide a closer, more manageable window into the processes that drive these colossal objects, such as the formation of jets and the dynamics of accretion disks. One of the most well-known microquasars in the Milky Way is SS433, located in the constellation Aquila. This system consists of a black hole and a companion star, and its jets have been observed to change direction over time, offering clues about the complex interactions between the black hole and its surroundings. Such observations help astronomers refine their understanding of how black holes influence their environments and how they evolve over time. But the mysteries of microquasars don't end there. These objects also challenge our understanding of physics, particularly when it comes to the behavior of matter under extreme conditions. The jets produced by microquasars are so powerful that they can accelerate particles to nearly the speed of light, creating conditions that are impossible to replicate on Earth. Studying these jets helps scientists test theories about relativity, particle acceleration, and the nature of space-time itself. As we continue to explore the Milky Way, microquasars remind us that even the smallest objects can hold the keys to understanding the universe's grandest mysteries. Next, we'll turn our attention to the galactic star bridges, vast structures that connect different parts of our galaxy in ways that defy expectations. Now, let's journey to one of the most breathtaking structures in the Milky Way, the galactic star bridges. These vast, luminous pathways of stars stretch across the galaxy, connecting distant regions in a cosmic web of light and gravity. Imagine a celestial highway not made of asphalt but of countless stars, gas, and dust, weaving together different parts of our galaxy in a stunning display of cosmic architecture. Galactic star bridges are formed through a combination of gravitational interactions and the remnants of ancient galactic collisions. When smaller galaxies or star clusters pass close to the Milky Way, their gravitational pull can stretch and distort the surrounding material, creating long, filament-like structures. Over millions of years, these filaments become populated with stars, forming the bridges we observe today. These structures are not just random collections of stars, they are the fingerprints of the Milky Way's dynamic and often violent history. One of the most famous examples of a galactic star bridge is the one connecting the Milky Way to the Large Magellanic Cloud, a nearby dwarf galaxy. This bridge, composed of stars and gas, was likely created by the gravitational tug of war between the two galaxies as they interacted over billions of years. Such bridges are not only beautiful to observe but also serve as critical tools for understanding how galaxies evolve and interact with their neighbors. The significance of galactic star bridges extends beyond their visual appeal. They act as cosmic pipelines, transporting gas, dust, and even stars from one region of the galaxy to another. This movement of material can trigger new star formation in areas that might otherwise remain dormant, effectively shaping the galaxy's structure and evolution. By studying these bridges, astronomers can piece together the history of galactic mergers and the forces that have shaped the Milky Way into the spiral galaxy we see today. But the mysteries of galactic star bridges don't end there. These structures also challenge our understanding of gravity and the large-scale structure of the universe. The way they form and persist over billions of years provides clues about the distribution of dark matter, the invisible substance that makes up most of the universe's mass. By mapping these bridges, scientists can infer the presence and behavior of dark matter, shedding light on one of the greatest mysteries in modern astrophysics. As we marvel at these cosmic connections, we're reminded of the intricate and interconnected nature of the universe. Galactic star bridges are not just relics of the past, they are active participants in the ongoing story of the Milky Way. Next, we'll explore the strange and fascinating world of galactic exoplanets, where planets defy expectations with their extreme conditions and unusual orbits. Now, let's turn our attention to the strange and fascinating world of galactic exoplanets, where planets defy expectations with their extreme conditions and unusual orbits. These distant worlds orbiting stars beyond our solar system challenge our understanding of planetary formation and behavior, offering a glimpse into the incredible diversity of the cosmos. One of the most intriguing examples is the exoplanet known as HD 189733b, a world where temperatures soar to nearly 2,000 degrees Fahrenheit and winds whip through its atmosphere at speeds of over 5,000 miles per hour. This planet, located about 63 light-years from Earth, is a vivid reminder of how extreme conditions can shape alien worlds. Its deep blue hue, caused by silicate particles in its atmosphere, might make it look like a serene ocean world from a distance, but in reality, it's a scorching, storm-ravaged inferno. Another remarkable discovery is the exoplanet WASP-12b, a planet so close to its star that it's being slowly torn apart. The intense gravitational forces from its host star have stretched the planet into an egg-like shape, and its atmosphere is being stripped away, creating a tail of gas that trails behind it. This process, known as tidal disruption, offers a rare opportunity to study how planets can be destroyed by their own stars, providing insights into the life cycles of planetary systems. Then there's the case of PSRB 1600-2026b, often referred to as the Methuselah planet. This exoplanet, located in the globular cluster Messier 4, is one of the oldest known planets in the Milky Way, estimated to be around 12.7 billion years old. Its existence challenges the idea that planets only form in younger star systems, suggesting that planetary formation might have occurred much earlier in the universe's history than previously thought. The discovery of these strange exoplanets has profound implications for our understanding of the galaxy. They reveal that planetary systems can form and evolve in ways that are vastly different from our own solar system. By studying these worlds, astronomers can piece together the conditions necessary for planet formation and the factors that lead to such extreme environments. These findings also raise intriguing questions about the potential for life in the universe. Could life exist on a planet with such extreme temperatures or chaotic orbits? While the conditions on many of these exoplanets seem inhospitable, they remind us that the universe is full of surprises. As we continue to explore the Milky Way, the study of strange exoplanets will undoubtedly uncover even more bizarre and fascinating worlds, expanding our understanding of the cosmos and our place within it. Next, we'll delve into the intriguing phenomenon of star clusters containing multiple generations of stars, where the past and present of stellar evolution collide in spectacular fashion. Now, let's shift our gaze to the captivating world of star clusters, where the past and present of stellar evolution coexist in a single, dazzling display. Among these, some of the most fascinating are star clusters that contain multiple generations of stars. These clusters, often referred to as multi-generational star clusters, challenge our traditional understanding of how stars form and evolve, offering a unique window into the complex processes that shape the cosmos. Typically, star clusters are thought to form in a single burst of star formation, with all their stars born around the same time from the same cloud of gas and dust. However, multi-generational star clusters defy this expectation. They contain stars of vastly different ages, some as old as billions of years and others as young as a few million years. This raises a compelling question. How can stars of such different ages exist in the same cluster? One leading theory suggests that these clusters experienced multiple waves of star formation. After the initial burst, the cluster may have retained enough gas and dust to fuel a second or even third round of star birth. This could happen if the cluster interacted with a nearby gas cloud, or if the first generation of stars produced enough material through stellar winds or supernova to trigger new star formation. The result is a cluster that tells the story of its own evolution, with older stars serving as relics of its early history and younger stars marking more recent events. A prime example of such a cluster is NGC 6791, located in the constellation Lyra. This cluster is estimated to be around 8 billion years old, yet it contains stars that are significantly younger. The presence of these younger stars suggests that NGC 6791 underwent multiple episodes of star formation, making it a living laboratory for studying how stars are born and evolve over time. Similarly, the globular cluster Omega Centauri, which we touched on earlier, also shows signs of containing stars of different ages, hinting at a complex and dynamic history. The existence of multi-generational star clusters has profound implications for our understanding of stellar evolution. They reveal that star formation is not always a one-time event but can occur in multiple phases, influenced by the environment and the life cycles of the stars themselves. These clusters also provide clues about the conditions necessary for star formation, such as the availability of gas and the role of gravitational interactions within the cluster. Moreover, studying these clusters helps astronomers piece together the timeline of star formation in the Milky Way. By analyzing the ages and compositions of stars within these clusters, scientists can trace the history of star birth in our galaxy and better understand how it has evolved over billions of years. This, in turn, sheds light on the broader processes that shape galaxies and the universe as a whole. As we continue to explore the Milky Way, multi-generational star clusters remind us that the cosmos is far more dynamic and interconnected than we once thought. They challenge us to rethink our assumptions and inspire us to uncover the secrets of stellar evolution. Next, we'll turn our attention to another enigmatic phenomenon, the mysterious gamma-ray pulsars that light up the galaxy with their high-energy emissions. Now, let's venture into the high-energy realm of the cosmos, where some of the most extreme objects in the Milky Way come to life. Among these are the mysterious gamma-ray pulsars, neutron stars that unleash powerful beams of gamma radiation into space. These pulsars are not only fascinating in their own right, but also hold the key to unlocking some of the deepest secrets of neutron stars and the forces that govern them. Pulsars are rapidly spinning neutron stars, the dense remnants of massive stars that have exploded in supernova. What makes gamma-ray pulsars unique is their ability to emit gamma rays, the most energetic form of light in the universe. Unlike regular pulsars, which primarily emit radio waves, gamma-ray pulsars shine brightly in the gamma-ray spectrum, making them some of the most luminous objects in the galaxy. The discovery of gamma-ray pulsars was a game-changer for astronomers. The first gamma-ray pulsar, known as the Geminga pulsar, was detected in the 1970s. Initially, it was thought to be a mysterious gamma-ray source with no visible counterpart. It wasn't until later that astronomers realized it was a pulsar, spinning rapidly and emitting gamma rays in precise clock-like intervals. This discovery opened up a new window into the study of neutron stars, revealing that they could produce energy in ways previously unimaginable. One of the most intriguing aspects of gamma-ray pulsars is their ability to accelerate particles to incredibly high speeds, producing gamma rays in the process. This happens near the pulsar's magnetic poles, where intense magnetic fields and rapid rotation create conditions ripe for particle acceleration. The gamma rays are then beamed into space, creating the pulsar's signature flashes of light. These beams can sweep across the galaxy like cosmic lighthouses, allowing astronomers to detect them from vast distances. Gamma-ray pulsars also provide valuable insights into the nature of neutron stars themselves. By studying their emissions, scientists can learn about the extreme conditions within these dense stellar remnants, including the behavior of matter under immense pressure and the strength of their magnetic fields. This information helps us understand not only how neutron stars work, but also how they influence their surroundings, from shaping the interstellar medium to triggering new star formation. One of the most famous gamma-ray pulsars is the Vela pulsar, located in the remnants of a supernova explosion. This pulsar emits gamma rays with incredible regularity, making it a prime target for studying the mechanisms behind these high-energy emissions. Another notable example is the Crab pulsar, which lies at the heart of the Crab Nebula. Its gamma-ray emissions have been studied extensively, providing a wealth of data on the processes that power these enigmatic objects. The study of gamma-ray pulsars has also shed light on the broader mysteries of the universe. For instance, they have been linked to the origins of cosmic rays, high-energy particles that travel through space at nearly the speed of light. By understanding how gamma-ray pulsars accelerate particles, scientists can piece together the puzzle of where cosmic rays come from and how they shape the cosmos. As we continue to explore the Milky Way, gamma-ray pulsars stand as a testament to the incredible diversity and complexity of the universe. They challenge our understanding of physics and inspire us to push the boundaries of what we know. Next, we'll turn our attention to another fascinating phenomenon, the streams of stars that trace the ancient collisions that have shaped our galaxy. Now, let's shift our gaze to the remnants of cosmic collisions that have left their mark on the Milky Way. These are the galactic star streams, vast rivers of stars that flow through our galaxy, tracing the paths of ancient encounters between the Milky Way and smaller galaxies. These streams are like cosmic fingerprints, revealing the violent and dynamic history of our galaxy's formation. Galactic star streams are formed when smaller galaxies or star clusters are torn apart by the Milky Way's immense gravitational pull. As these smaller systems are disrupted, their stars are stretched into long, flowing arcs that orbit the galaxy. Over billions of years, these streams become intertwined with the Milky Way's structure, creating a tapestry of stars that tells the story of our galaxy's past. One of the most well-known examples is the Sagittarius Stream, a vast ribbon of stars that wraps around the Milky Way. This stream is the remnant of the Sagittarius dwarf spheroidal galaxy, a small satellite galaxy that has been slowly consumed by the Milky Way over billions of years. The stars in this stream are a testament to the relentless pull of gravity and the ongoing process of galactic cannibalism. Studying these star streams provides astronomers with a unique window into the Milky Way's history. By mapping the positions and motions of the stars within these streams, scientists can reconstruct the events that led to their formation. This includes determining when and how the Milky Way collided with smaller galaxies, as well as understanding the distribution of dark matter, which plays a crucial role in shaping these streams. The significance of galactic star streams extends beyond just understanding the Milky Way's past. They also offer insights into the nature of dark matter, the invisible substance that makes up most of the universe's mass. The way these streams are shaped and distributed can reveal the presence and distribution of dark matter in the Milky Way, helping scientists refine their models of how galaxies form and evolve. Another fascinating aspect of these streams is their connection to the Milky Way's future. As the galaxy continues to grow by consuming smaller systems, new star streams will form, adding to the complex web of stellar rivers that already exist. This ongoing process highlights the dynamic and ever-changing nature of our galaxy, reminding us that the Milky Way is far from a static entity. One of the most intriguing discoveries in recent years is the Gaia Sausage, a massive star stream that represents the remnants of a dwarf galaxy that collided with the Milky Way around 10 billion years ago. This collision was so significant that it may have contributed to the formation of the Milky Way's thick disk, a region of stars that lies above and below the galaxy's main plane. The Gaia Sausage is a prime example of how ancient collisions have shaped the Milky Way into the galaxy we see today. As we continue to explore these star streams, we uncover more about the forces that have shaped our galaxy over billions of years. They are a reminder that the Milky Way is not just a collection of stars but a living, evolving system, shaped by countless interactions and collisions. Next, we'll delve into the final mystery on our list, the strange signatures of dark energy that may be hidden within our galaxy. Now, as we approach the final mystery on our journey through the Milky Way, we turn our attention to one of the most enigmatic forces in the cosmos, dark energy. This invisible and mysterious energy is believed to be driving the accelerated expansion of the universe, but could its signatures also be hidden within our own galaxy? Let's explore the strange possibility of detecting dark energy within the Milky Way and what it could mean for our understanding of the universe. Dark energy is a term used to describe the unknown force that makes up about 68% of the universe's total energy content. Unlike dark matter, which exerts a gravitational pull, dark energy appears to work in the opposite way, pushing galaxies apart and causing the universe to expand at an ever-increasing rate. While its effects are most noticeable on the largest scales, scientists have begun to wonder if traces of dark energy could also be detected closer to home within the Milky Way. One of the key challenges in studying dark energy is that it doesn't interact with light or matter in any way we can directly observe. Instead, its presence is inferred through its effects on the universe's expansion. However, recent research has suggested that subtle signatures of dark energy might be detectable within the Milky Way by studying the motions of stars and the distribution of matter. For example, if dark energy is influencing the galaxy's structure, it could cause slight deviations in the orbits of stars or the way gas clouds move through space. Another intriguing possibility is that dark energy could be linked to the mysterious voids and underdense regions within the Milky Way. These are areas where the density of stars and gas is much lower than average, and some scientists speculate that dark energy might play a role in creating or shaping these voids. By mapping these regions and analyzing their properties, astronomers hope to uncover clues about the nature of dark energy and how it interacts with the fabric of space-time. The significance of detecting dark energy within the Milky Way would be profound. It would not only provide a new way to study this elusive force, but also offer insights into how it operates on smaller scales. This could help bridge the gap between the large-scale effects of dark energy observed in the distant universe and the local dynamics of our own galaxy. Understanding dark energy is crucial because it holds the key to the ultimate fate of the universe, determining whether the cosmos will continue to expand forever or eventually collapse back in on itself. As we conclude our exploration of the 50 strange objects in the Milky Way, it's clear that our galaxy is a treasure trove of mysteries, from the remnants of ancient collisions to the subtle whispers of dark energy. Each discovery brings us closer to understanding not just the Milky Way, but the universe as a whole. If you've enjoyed this journey through the wonders of our galaxy, don't forget to like, subscribe, and hit the notification bell for more cosmic adventures. Until next time, keep looking up and wondering about the endless mysteries that await us in the stars. As we wrap up our journey through the 50 strange objects in the Milky Way, it's impossible not to marvel at the sheer diversity and mystery our galaxy holds. From the cannibalistic stars of Omega Centauri to the ghostly whispers of dark energy, each discovery has peeled back another layer of the cosmic enigma that surrounds us. These objects, each with their own unique story, remind us that the Milky Way is far more than just a collection of stars. It's a dynamic, ever-evolving tapestry of wonders that challenges our understanding of the universe. What ties these 50 strange objects together is their ability to spark curiosity and push the boundaries of what we know. Whether it's the runaway stars racing across the galaxy or the eerie silence of rogue planets drifting in the void, each one offers a glimpse into the forces that shape our cosmic home. They remind us that even in our own backyard, there are mysteries waiting to be unraveled, questions begging to be answered, and stories yet to be told. But the journey doesn't end here. Every discovery raises new questions, and every answer leads to more mysteries. The Milky Way is a living, breathing entity, constantly changing and surprising us. And as we continue to explore, we're not just learning about the galaxy, we're learning about ourselves and our place in the vast expanse of the cosmos. If you've enjoyed this cosmic adventure, don't forget to share your thoughts in the comments below. Which of these strange objects fascinated you the most? Let's keep the conversation going. And if you want to dive deeper into the wonders of the universe, hit that subscribe button and ring the notification bell so you never miss out on our next exploration. Until then, keep your eyes on the stars and your mind open to the endless possibilities that lie beyond. The universe is waiting, and the mysteries of the Milky Way